Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the story of Three-Eye Atlas, a visitor from the stars that cross the vast emptiness between suns to briefly grace our solar system with its ancient presence. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The discovery begins on a September night in 2024, when automated telescopes scanning the southern sky register a faint smudge of light moving against the fixed stars. The object appears unremarkable at first, just another dim point creeping slowly across the constellation of Sculptor, barely brighter than the background glow of distant galaxies. Magnitude 19.5, so faint that human eyes could never detect it even through the largest telescopes. Yet, something in its motion catches the attention of the computer algorithms that sift through thousands of images each night, searching for anything that moves, brightens, or changes in the cosmic dark. The Atlas survey system, with its twin telescopes perched on Hawaiian mountaintops, captures the visitor's ghostly passage through a field of stars that have watched over Earth for millennia. Each exposure lasts 30 seconds, long enough for the electronic sensors to gather sufficient photons to reveal objects millions of times fainter than what ancient astronomers could see with naked eyes. Between one image and the next, taken 20 minutes later, the object has shifted by a few pixels, movement so subtle it would escape human notice, but unmistakable to software designed to detect exactly such wandering lights. Observatory staff in Chile and South Africa confirmed the detection within hours, their instruments tracking this wandering speck as it drifts through the outer reaches of the solar system. The Catalina Sky Survey joins the hunt, followed by telescopes across 6 continents, all turning their electronic eyes toward this barely perceptible visitor. The object moves with purpose, following a trajectory that carries it steadily inward toward the sun, but at angles and speeds that immediately mark it as unusual among the usual population of asteroids and comets. Its path cuts across the orbital planes of the outer planets at an inclination of nearly 60 degrees, a trajectory that suggests origins far from the ecliptic plane where most solar system objects travel their predictable circuits. This is no ordinary asteroid following the gravitational grooves carved by billions of years of planetary influence. Nor is it a periodic comet returning from the Kuiper Belt's distant icy realms. Something about its motion speaks of deeper origins, of journeys measured not in decades or centuries, but in geological ages. Initial measurements reveal a nucleus perhaps 2 kilometers across, slightly elongated like so many small bodies that tumble through space. Its surface reflects only 4% of the sunlight that strikes it, darker than charcoal. Darker even than the carbonaceous asteroids that represent some of the most primitive matter in the solar system. This darkness hints at ancient organic compounds, carbon-rich materials that may have been cooking in the radiation fields between stars for millions of years, gradually darkening like cosmic soot. Yet, even in these early observations, astronomers notice something peculiar about its spectrum. The light it reflects carries subtle signatures that don't quite match the expected fingerprints of objects born in our solar system's outer regions. The ice seems older somehow, formed under conditions slightly different from those that prevailed in the primordial disk that gave birth to the planets. Trace elements appear in proportions that suggest formation around a star with a different metallicity, a different balance of heavy elements forged in stellar cores and scattered by ancient supernovae. Only when orbital calculations begin does the true nature of this visitor become clear. The mathematics are unforgiving in their precision, each observation adding constraints that narrow the possibilities until only one conclusion remains. This object follows a hyperbolic trajectory, an open curve that carries it on a one-way journey through the solar system. Its orbital eccentricity measures 1.2, meaning it moves too fast for solar gravity to capture it permanently. It has come from somewhere else, from the vast spaces between the stars, and after its brief encounter with our Sun, it will continue outward into the galactic dark, never to return. The realization settles over the astronomical community like a quiet revelation. Here, captured in their telescopes, moves a piece of another stellar system, a fragment of ice and rock that condensed around a different star, in a different planetary disk, perhaps billions of years ago. It has traveled through the galactic night for longer than complex life has existed on Earth, drifting in the cold and dark until solar gravity finally captured it in this gentle arc through the inner system. Teams around the world begin coordinating observations, their instruments turning toward this cosmic wanderer with the focused attention usually reserved for the most significant celestial events. The European Southern Observatory redirects its very large telescope array. The Hubble Space Telescope adjusts its pointing schedule. Radio telescopes listen for any unusual emissions, though none expects to hear signals from this ancient traveler. Infrared detectors measure its temperature as solar heat begins to warm its surface for the first time in eons. Spectrometers analyze every photon of reflected sunlight, searching for clues about the distant stellar nursery where this traveler first took shape. Each wavelength carries information absorption lines that reveal the presence of water ice, carbon dioxide, and more complex organic molecules. The ratios of isotopes may tell stories about nuclear processes in its parent star, about the particular mix of elements that were available when this comet condensed from primordial gas and dust in some distant solar nebula. The object receives its official designation, 3-way Atlas, marking it as the third confirmed interstellar comet and crediting the Atlas survey system that first detected its motion. The I stands for Interstellar, a classification created only recently as astronomers have begun to recognize these visitors from the deep. Before 2017, no confirmed interstellar objects had ever been detected passing through the solar system. Now, with improving survey capabilities and more sensitive instruments, they appear perhaps once every few years messengers from the galactic community carrying news of distant worlds. But already, in the careful language of scientific papers and observation requests, 3I Atlas carries a deeper significance than mere astronomical curiosity. This represents humanity's first opportunity to study, up close and in detail, material that formed around another star. Every measurement adds to the growing library of knowledge about planetary formation beyond the solar system, about the chemical and physical processes that govern the birth of worlds throughout the galaxy. Night after night, the telescopes track its steady progress inward. The comet brightens gradually as solar radiation begins to sublimate the ancient ices locked within its nucleus. Somewhere in the darkness ahead of its path lies perihelion, the moment of closest approach to the Sun, when this visitor from deep space will experience the warmth of our star for the first and final time in its long existence. Amateur astronomers join the watch, their smaller telescopes adding to the global network of observers. Photography enthusiasts capture long-exposure images that show the comet as a faint smudge moving against star fields. Social media fills with images and speculation. As humanity collectively witnesses the passage of this cosmic messenger, only now, in the 21st century, Do we possess the technology to detect such faint visitors and the computational power to quickly determine their exotic origins? The discovery marks a moment of transition in human understanding. We are no longer isolated observers of our own solar system, but witnesses to the larger galactic community of which our Sun is just one modest member. Each interstellar visitor carries with it the chemical fingerprints of distant stellar neighborhoods, expanding our knowledge of planetary formation and stellar evolution beyond the narrow sample provided by our own cosmic backyard. The orbital mathematics unfold like an ancient theorem, each new measurement adding precision to calculations that reveal the comet's impossible journey. Astronomers feed positional data into computer models that trace the object's path backward through time, following gravitational breadcrumbs toward its point of origin. The numbers tell a story that stretches across geological ages. This wanderer has been traveling for longer than the Himalayas have stood, longer than the Atlantic Ocean has been widening, perhaps even longer than multicellular life has flourished on Earth. The comet's velocity relative to the Sun measures 26 kilometers per second, fast enough to cross the continental United States in less than 3 minutes, yet barely a whisper compared to the speeds at which galaxies recede from one another in the expanding universe. This velocity lies at the heart of the mystery, for it exceeds the escape velocity needed to break free from solar gravity by a comfortable margin. No gravitational slingshot from Jupiter or Saturn could have accelerated a solar system native to such speeds. The object must have arrived from interstellar space, already moving at this breakneck pace. Refined observations narrow the uncertainty in its trajectory to mere kilometers across distances measured in astronomical units. The comet approaches the Sun from the direction of the constellation Lyra. Though this represents only its most recent heading through the galaxy's rotating spiral arms, tracing its path further backward becomes an exercise in cosmic archaeology, requiring models of galactic rotation, stellar motions, and the complex gravitational dance of hundreds of billions of stars moving through space in their own individual orbits around the galaxy's center. Computer simulations run for days, integrating the equations of motion through millions of years of galactic history. The calculations must account for the Sun's own motion through space. Our star carries the entire solar system on a circuit around the galactic center that takes roughly 230 million years to complete. During this grand orbital period, the Sun rises and falls through the galaxy's disk like a cosmic carousel horse, encountering different stellar neighborhoods and varying densities of interstellar matter. The models suggest that 3A Atlas may have originated from a stellar system somewhere in the direction of Vega, though the uncertainties span dozens of light years and millions of years. Perhaps it condensed in the outer regions of a planetary disk around a star slightly more massive than our Sun, a star that burned brighter and evolved faster, eventually swelling into a red giant and dispersing its family of comets into the interstellar void. Or perhaps it formed around a smaller, cooler star, only to be ejected by gravitational encounters with passing stellar neighbors or the tidal forces exerted by nearby molecular clouds. The galactic context adds layers of complexity to the comet's biography. Our solar system currently occupies a relatively quiet region of the galaxy's Orion arm, a minor spiral feature between the major Perseus and Sagittarius arms. But over the millions of years that 3I Atlas has been traveling, it may have crossed through regions of much higher stellar density, navigating gravitational fields shaped by massive star clusters, giant molecular clouds, and the turbulent environments surrounding stellar nurseries where new suns are born. Astronomers calculate that roughly one interstellar object larger than a meter should pass through the inner solar system each year, though most remain too faint to detect with current technology. The galaxy teems with such wanderers, comets and asteroids ejected from their birth systems by planetary migrations. stellar encounters, or the violent deaths of massive stars. They form a kind of galactic ecosystem, carrying materials between stellar systems and mixing the chemical products of stellar evolution across vast distances. The discovery of 3I Atlas represents just the visible tip of this cosmic iceberg. For every interstellar visitor we detect, thousands more pass through unnoticed. Too small or too distant to register on our instruments, they comprise a vast population of nomadic worlds, following hyperbolic trajectories that carry them on one-way journeys between the stars. Some may travel for billions of years before encountering another stellar system, aging slowly in the cosmic cold while the galaxy completes multiple rotations around them. What makes 3I Atlas particularly intriguing to orbital dynamicists is its relatively low velocity compared to other confirmed interstellar objects. While Oumuamua, the first detected interstellar visitor, moved at nearly twice the speed, 3I Atlas travels at velocities that suggest a more sedate ejection from its parent system. This may indicate that it originated from the outer regions of its birth system's Comet cloud, gently nudged into interstellar space rather than violently expelled by close gravitational encounters. The comet's orbital inclination, the angle at which its trajectory tilts relative to the ecliptic plane, provides additional clues about its origins. Most solar system objects orbit within a few degrees of the ecliptic, reflecting their formation from a flattened disk of material around the young sun. But 3I Atlas approaches at an angle of nearly 60 degrees, consistent with arrival from a random direction in three-dimensional space. This geometric signature marks it unmistakably as an outsider, unbound by the gravitational architecture that shapes the motions of solar system natives. As the weeks pass and more observations accumulate, the orbital solution becomes increasingly precise. Ground-based telescopes around the world contribute measurements, their combined efforts reducing the uncertainty in the comet's position to mere arc-seconds across the sky. Space-based observatories add their own data, free from the atmospheric turbulence that limits ground-based precision. Each measurement represents a small victory in humanity's ongoing effort to map the cosmos with ever greater accuracy. The International Astronomical Union's Minor Planet Center becomes the clearinghouse for these observations, collecting data from dozens of observatories and computing increasingly refined orbital elements. The center's computers run continuously, updating the comet's predicted position as new measurements arrive and distributing ephemeris data to observatories worldwide. This global coordination represents one of astronomy's great collaborative achievements, the ability to track objects across the solar system with unprecedented precision. Perhaps most remarkably, the orbital calculations reveal that 3I Atlas will remain visible to Earth-based telescopes for many months, allowing detailed study of this cosmic visitor as it approaches and then recedes from the Sun. Unlike Oumuamua, which was discovered only after it had already rounded the Sun and begun its exit from the solar system, 3I Atlas offers astronomers the luxury of time to plan comprehensive observational campaigns, time to develop new techniques for studying interstellar objects, and time to watch as solar heat gradually transforms this ancient wanderer from a dark, inert nucleus into an active comet trailing gas and dust across millions of kilometers of space. The mathematics that describe its motion also predict its future after completing its single loop around the Sun. 3I Atlas will depart the solar system in the direction of the constellation Telescopium, carrying with it whatever subtle changes its brief encounter with solar radiation may have wrought. It will spend the next several million years crossing the largely empty spaces between stellar systems, gradually cooling back toward the cosmic background temperature of -270 degrees Celsius, waiting for another chance encounter with a distant star. Spectroscopic analysis begins almost immediately after the discovery. As astronomers turn their most sensitive instruments toward this messenger from the depths of space, the light reflected from 3I Atlas carries within it the chemical fingerprints of materials forged in stellar furnaces billions of years ago, condensed in the cold outer reaches of an alien planetary system, and aged in the radiation fields between stars for longer than complex life has existed on Earth. Each wavelength tells part of the story, revealing molecular signatures that speak of water ice, carbon compounds, and the primordial dust that forms the backbone of all rocky worlds. The initial spectroscopic observations reveal absorption features characteristic of water ice mixed with darker, more complex materials. Infrared telescopes detect the distinctive signatures of H2O molecules vibrating in their crystalline lattices, confirming that this visitor carries the same life-giving compound that fills Earth's oceans and flows through every living cell. Yet the water ice appears different. Somehow, its spectral signature suggests formation at temperatures and pressures slightly different from those that prevailed in our own solar system's early history. Deeper analysis reveals the presence of carbon dioxide ice frozen into the comet's structure during its formation around a distant star. This CO2 exists as a separate phase from the water ice, creating a layered structure that speaks of complex thermal processes during the object's condensation from the primordial disk. The ratio of carbon dioxide to water differs subtly from that observed in solar system comets, hinting at formation conditions where carbon was either more or less abundant relative to oxygen than in our own cosmic neighborhood. More exotic compounds emerge from the spectroscopic data as observations accumulate. Astronomers detect hints of carbon monoxide ice, a volatile compound that sublimates at even lower temperatures than carbon dioxide. The presence of CO suggests that 3I Atlas formed in the coldest regions of its parent system, where temperatures dropped below -230 degrees Celsius, cold enough to freeze this normally gaseous molecule into solid form. Such extreme cold exists only in the outermost reaches of planetary systems, far beyond the orbit of any potentially habitable worlds. Trace amounts of methane ice appear in the longer wavelength infrared observations, though in concentrations much lower than those found in solar system comets originating from the Kuiper belt. This relative depletion of methane may reflect the comet's extended journey through interstellar space, where cosmic radiation gradually breaks down the most fragile organic molecules over millions of years. What remains represents the most chemically robust components of the original condensate materials, hardy enough to survive eons of bombardment by high-energy particles streaming through the galaxy. The darker, non-icy components prove more challenging to identify, but gradually yield their secrets to persistent observation. Complex carbon compounds dominate the refractory materials, creating the dark surface that reflects only a few % of incident sunlight. These organics likely form through radiation processing of simpler carbon-bearing molecules, a slow cooking process that occurs whenever organic matter spends extended periods exposed to cosmic rays and ultraviolet starlight. The result resembles the dark, tarry materials found in carbonaceous meteorites, but aged and processed by millions of years in the interstellar environment. Silicate minerals provide the rocky framework within which the ices and organics are embedded. Spectroscopic features reveal the presence of olivine and pyroxene, the same magnesium and iron silicates that form the backbone of rocky planets throughout the galaxy. These minerals appear to have crystallized at high temperatures, possibly in the hot inner regions of the comet's birth system, before being transported outward and incorporated into the growing nucleus. Their presence suggests that even this icy wanderer contains materials forged in the intense heat near its parent star. Perhaps most intriguing are the isotopic ratios revealed by high-resolution spectroscopy. The abundance of heavy hydrogen deuterium relative to ordinary hydrogen provides clues about the temperature and environment where the comet's water first condensed. Initial measurements suggest a deuterium to hydrogen ratio different from that found in Earth's oceans or in most solar system comets, though the uncertainties remain large. This isotopic signature may preserve information about the nuclear processes occurring within the comet's parent star, or about the particular mix of interstellar materials from which its planetary system formed. The nitrogen isotope ratio tells another part of the story, revealed through observations of trace amounts of ammonia, ice, mixed with the water and carbon dioxide. The ratio of nitrogen-15 to nitrogen-14 appears consistent with formation in an environment where stellar nucleosynthesis proceeded slightly differently than in our own sun's stellar neighborhood. These subtle differences accumulate over billions of years as successive generations of stars enrich the interstellar medium with the products of their nuclear fusion, creating regional variations in isotopic composition that serve as chemical fingerprints of galactic neighborhoods. Sulfur compounds add another layer of complexity to the comet's composition. Hydrogen sulfide ice appears in small quantities, contributing to what will eventually become the comet's characteristic odor as solar heating begins to sublimate these volatile materials. The sulfur likely originated in the stellar winds of the comet's parent star, incorporated into the growing planetary disk, and eventually condensed into solid form in the cold outer regions where 3I Atlas took shape. Metal oxides contribute trace constituents that speak of the dust grains around which the comet first accreted. Iron oxides, aluminum oxides, and magnesium oxides appear in spectroscopic observations, representing the refractory cores of the original condensation nuclei. These materials formed at temperatures exceeding 1,000 degrees Celsius, either in stellar atmospheres or in the shock waves of exploding supernovae, before cooling and serving as seeds for the growth of larger particles in the protoplanetary disk. The overall composition paints a picture of formation around a star with a metallicity abundance of heavy elements slightly different from our Sun's. The parent star may have been enriched in the products of earlier stellar generations, creating a protoplanetary disk with subtly different proportions of rock-forming elements, volatiles, and organic precursors. These differences, preserved in the comet's structure for millions of years, offer a direct sample of stellar and planetary formation processes in another part of the galaxy. As spectroscopic observations continue, astronomers begin to piece together the comet's thermal history. The crystalline structure of the water ice suggests episodes of heating and cooling that annealed the originally amorphous ice into more ordered forms. This thermal processing may have occurred during the comet's formation, as radioactive decay of short-lived isotopes warmed the interior, or during its long journey through interstellar space, as encounters with shock waves from distant supernovae or stellar winds periodically raised its temperature above the crystallization threshold. Most remarkably, the composition of 3I Atlas appears broadly similar to solar system comets, despite its exotic origins. This suggests that the fundamental processes governing planetary formation, gas and dust condensation, accretion of planetesimals, and the migration of volatile-rich objects to outer system reservoirs operate in similar ways throughout the galaxy. The comet represents not just a visitor from another star, but confirmation that the chemical and physical processes we observe in our own solar system reflect universal principles governing the formation of planetary systems around other stars. The journey that brought 3I Atlas to our solar system spans a duration so vast that human minds struggle to comprehend its true magnitude. For approximately 4 million years, this wanderer has drifted through the near-perfect vacuum between stars, crossing distances measured in parsecs while experiencing temperatures just a few degrees above absolute zero. During this cosmic voyage, entire species have evolved and vanished on Earth. Ice ages have come and gone, and the continents have shifted measurably across the planet's surface. Yet through all these terrestrial transformations, the the comet has maintained its solitary course through the galactic night, following gravitational currents too subtle for any single star to dominate. The interstellar medium through which 3I Atlas has traveled represents one of the most extreme environments in the universe, a near vacuum containing perhaps 1 atom per cubic centimeter, compared to the trillion atoms that occupy the same volume of air at Earth's surface. This tenuous gas consists primarily of hydrogen and helium, the primordial elements forged in the first few minutes after the Big Bang, mixed with heavier elements scattered by countless stellar explosions over billions of years. Embedded within this sparse matter are microscopic dust grains, organic molecules, and the occasional dense cloud where new stars will eventually be born. Despite its apparent emptiness, interstellar space pulses with energy in forms both subtle and violent. Cosmic rays, high-energy particles accelerated by supernova shockwaves, and other cosmic catastrophes stream through the void at nearly the speed of light, carrying energies millions of times greater than anything produced in terrestrial particle accelerators. These cosmic bullets have been steadily bombarding 3I Atlas throughout its journey, gradually altering its surface chemistry and creating new molecular species through radiation-induced reactions. The outer layers of the comet bear the accumulated scars of this bombardment, darkened and chemically modified by millions of years of exposure to galactic radiation. Magnetic fields thread through the interstellar medium like invisible highways, channeling the flow of charged particles and creating complex patterns of force that extend across light years. These fields originate from various sources: the rotation of massive stars, the explosive deaths of stellar giants, and the slow churning of gas within spiral arms. As 3I Atlas moved through these magnetic domains, it experienced subtle forces that may have influenced its trajectory over geological timescales, nudging it gradually toward its eventual encounter with our solar system. Temperature fluctuations punctuated the comet's otherwise frigid journey as it passed through regions of varying density and energy. Most of interstellar space maintains a temperature near 10 Kelvin, just 10 degrees above absolute zero, but shockwaves from distant stellar explosions can temporarily heat local regions to thousands of degrees. These thermal pulses, lasting perhaps thousands of years, may have caused subtle changes in the comet's structure as different ices expanded and contracted at different rates, creating internal stresses that fractured the nucleus or redistributed volatile materials between surface and interior. The comet's path carried it through at least one spiral arm of the galaxy, and possibly two, as it made its way from its origin point toward our solar system. These spiral arms represent regions of enhanced stellar density, where massive young stars burn brightly and die violently, enriching the surrounding medium with heavy elements and energy. Passage through a spiral arm would have exposed 3I Atlas to increased levels of radiation and gravitational perturbations, potentially altering its trajectory and accelerating the chemical evolution of its surface materials. Gravitational encounters with other stellar systems may have influenced the comet's path during its interstellar wandering. Computer simulations suggest that 3I Atlas likely passed within several light years of other stars during its journey, experiencing gravitational tugs too weak to capture it, but strong enough to modify its velocity by small amounts. These encounters accumulate over millions of years, gradually bending the comet's trajectory through three-dimensional space in ways that make its ultimate origin difficult to pinpoint with certainty. The vacuum through which the comet traveled exists in a state of perpetual motion, with different regions streaming past one another at velocities of tens of kilometers per second. These bulk motions reflect the galaxy's rotation, the expansion of supernova-heated bubbles, and the gravitational influence of massive stellar associations. 3I Atlas moved through this dynamic medium like a slow-moving boat navigating ocean currents, its trajectory influenced by forces operating on scales far larger than individual stellar systems. Molecular clouds dense regions where interstellar gas concentrates enough to eventually form new stars marked significant waypoints along the comet's route. These clouds contain materials cold enough to freeze even hydrogen into solid form, creating environments where complex organic chemistry can proceed despite the harsh conditions of space. Passage through or near such clouds may have deposited additional materials onto the comet's surface, or stripped away loosely bound volatiles through collisions with dust grains moving at high relative velocities. The galaxy's magnetic field provided a vast coordinate system through which 3 Atlas navigated its journey. This field, generated by the rotation of charged gas within the galactic disk, creates patterns that extend across thousands of light-years and persist for millions of years. Charged particles within the comet's nucleus would have aligned themselves with local field directions, creating microscopic compasses that recorded the magnetic environments encountered during the long voyage. Tidal forces from the galaxy's overall gravitational field acted on the comet throughout its journey, though their effects remained almost imperceptibly small over such a compact object. These forces reflect the galaxy's non-uniform distribution of matter, the central black hole, spiral arm concentrations, and dark matter halo, all contributing to gravitational gradients that stretch and squeeze objects moving through galactic space. For 3I Atlas, these tidal effects amounted to stresses measured in millionths of Earth's surface gravity, insignificant compared to the comet's own internal cohesion. Radio waves from natural cosmic sources, pulsars, stellar coronae, and the faint afterglow of the Big Bang washed over the comet throughout its journey, carrying information about distant astrophysical processes. While these radio signals could not significantly affect the comet's structure or trajectory, they represent a constant background of electromagnetic energy that pervades all of space. 3I Atlas moved through this radio sea like a silent listener, absorbing and scattering these signals according to the electrical properties of its surface materials. Dust impacts provided another form of interaction with the interstellar medium, as microscopic grains moving at high relative velocities struck the comet's surface like cosmic sandblasting. Each impact, though involving only nanograms of material, released energies equivalent to small explosions, gradually eroding the surface and exposing fresh materials beneath. Over millions of years, this process removed perhaps several meters of material from the comet's surface, revealing subsurface layers that formed under different conditions during its original accretion. The comet's slow tumbling motion, inherited from gravitational interactions during its ejection from its parent system, carried it through space in a complex rotational dance. This tumbling exposed all surfaces to the interstellar environment over time scales of hours to days, ensuring that radiation processing and dust erosion affected the entire nucleus rather than just one hemisphere. The tumbling rate may have changed slightly over millions of years as dust impacts and radiation pressure exerted tiny torques on the irregular nucleus. Perhaps most remarkably, 3I Atlas maintained its structural integrity throughout this extended journey, held together by the weak gravitational attraction between its constituent particles and the molecular bonds within its icy matrix. The comet represents a testament to the remarkable stability that can exist even in the harsh environment of interstellar space, where objects must rely entirely on their own internal cohesion to survive encounters with radiation, dust, magnetic fields, and the subtle but persistent forces that shape the galaxy's evolution across cosmic time. The boundary between interstellar space and the solar system exists not as a sharp edge, but as a gradual transition zone where two very different physical environments slowly blend into one another. This region, known as the heliopause, marks the distance at which the solar wind, a stream of charged particles flowing outward from the Sun at hundreds of kilometers per second, finally succumbs to the pressure of the interstellar medium. For 3I Atlas, crossing this invisible threshold represents the first significant change in its environment in millions of years, as the comet encounters the magnetic fields and particle streams that define our star's sphere of influence. The solar wind originates in the Sun's corona, where temperatures exceed 1 million degrees Celsius, and the star's magnetic field can no longer contain the expanding plasma. Electrons and protons, along with heavier ions torn from stellar material, stream outward at velocities approaching the speed of sound in the tenuous coronal gas. This wind carries with it tangled magnetic field lines that spiral outward as the Sun rotates, creating a vast magnetic structure that extends far beyond the orbits of the planets. By the time this solar material reaches the heliopause, roughly 120 astronomical units from the Sun, it has cooled and thinned considerably, but still maintains enough pressure to hold back the flow of interstellar matter. As 3I Atlas approaches this boundary from the galactic void, the first signs of solar influence appear as subtle changes in the charged particle environment. Cosmic rays that have bombarded the comet for millions of years begin to decrease in intensity as the solar magnetic field deflects some of these high-energy particles away from the inner solar system. This cosmic ray modulation creates the first detectable signature of the comet's approach to a stellar environment. Though the changes remain too subtle to affect the comet's structure or composition in any measurable way, the interstellar magnetic field, aligned roughly with the direction of the solar system's motion through the galaxy, begins to interact with the expanding solar magnetic field in complex ways. These two magnetic domains compress against each other like colliding soap bubbles, creating regions of enhanced field strength and occasional reconnection events where magnetic field lines snap and reconfigure themselves. Such reconnection can accelerate particles to high energies and generate bursts of electromagnetic radiation, though these phenomena occur on scales too large to directly affect a small object like 3I Atlas. Temperature variations mark another signature of the heliospheric boundary, though the changes remain almost imperceptible in the near-absolute zero environment of outer space. The solar wind, despite its high temperature at the Sun, has cooled to just a few 100,000 degrees by the time it reaches the heliopause. Even this relatively modest heating represents a significant increase compared to the 10-degree temperature of the local interstellar medium, creating thermal gradients that extend across billions of kilometers of space. Charged dust grains scattered throughout the outer solar system begin to influence the electromagnetic environment as 3I Atlas penetrates deeper into the heliosphere. These particles, ranging in size from nanometers to micrometers, carry electrical charges acquired through interactions with solar radiation and the solar wind. Their collective behavior creates a tenuous plasma that modifies the propagation of electromagnetic waves and alters the local electrical properties of space. For an object like 3I Atlas, composed primarily of neutral atoms and molecules, these effects remain largely irrelevant, but they contribute to the growing complexity of the physical environment surrounding the comet. The solar wind's dynamic pressure begins to exceed that of the interstellar medium as 3I Atlas moves inward past the heliopause. This pressure, though equivalent to only a few billionths of atmospheric pressure at Earth's surface, becomes sufficient to influence the motion of small dust particles and to shape the trajectories of other charged materials in the outer solar system. The comet itself, massive enough to be unaffected by such subtle forces, continues on its gravitationally determined path. But the environment through which it travels has fundamentally changed character. Variations in solar activity create ripples that propagate outward through the heliosphere at the speed of the solar wind, taking months or years to reach the heliopause boundary. solar flares, coronal mass ejections, and the 11-year solar magnetic cycle all leave their signatures in the structure and dynamics of the outer heliosphere. As 3I Atlas crosses this boundary, it enters a region where the influence of our star's magnetic variability creates a constantly changing environment. Though these changes occur too slowly and on scales too large to affect the comet's immediate behavior, the transition zone itself spans several astronomical units, creating a gradual shift from interstellar to solar-dominated conditions rather than an abrupt boundary. Within this region, the properties of space fluctuate as parcels of solar and interstellar material mix and interact. Magnetic field directions shift gradually. Particle densities vary by factors of 2 or 3, and temperature profiles reflect the complex interplay between solar heating and interstellar cooling. 3I Atlas traverses this transition zone over a period of several months, experiencing the first changes in its environment since departing its distant stellar birthplace. Bow shock phenomena may mark the comet's passage through regions where the solar wind encounters obstacles such as dense clouds of interstellar material or the magnetic fields of other celestial bodies. These shock waves, similar to the sonic booms created by supersonic aircraft, compress and heat the surrounding plasma while deflecting particle flows around the obstruction. Though 3I Atlas itself is too small to generate significant bow shocks, it may encounter the wake regions behind larger obstacles, experiencing brief episodes of altered magnetic field orientation and particle flux. The galactic cosmic ray environment continues to evolve as the comet penetrates deeper into the heliosphere. Solar magnetic fields provide increasingly effective shielding against lower energy cosmic rays, while higher energy particles continue to penetrate toward the inner solar system with little deflection. This energy-dependent modulation creates subtle changes in the radiation environment that may influence the rate of surface chemistry on the comet's nucleus. Though such effects would require sensitive laboratory analysis to detect, neutral atoms from the interstellar medium continue to flow through the heliosphere largely unimpeded by magnetic fields, creating a population of interstellar material that penetrates deep into the solar system. These atoms include hydrogen, helium, oxygen, and nitrogen from the local interstellar cloud, carrying chemical signatures that differ subtly from solar system materials. As 3I Atlas moves through this neutral component of the interstellar medium, it encounters familiar materials in unfamiliar proportions, representing a bridge between its interstellar origins and its solar system destination. The solar gravitational field begins to dominate other forces as the comet approaches the outer planet's realm. While gravitational effects extend infinitely through space, the Sun's influence becomes increasingly important as 3I Atlas moves inward and other stellar gravitational fields fade into insignificance. This transition marks not just a change in the comet's physical environment, but the beginning of its temporary capture by our solar system's gravitational architecture. The ancient wanderer has found a new, if temporary, gravitational home. Plasma waves generated by various solar system processes begin to propagate through the medium surrounding the comet's trajectory. These waves, analogous to sound waves but traveling through the charged particle environment rather than through ordinary matter, carry energy and information across vast distances. Radio telescopes on Earth can detect some of these natural radio emissions, providing remote sensing capabilities that will eventually contribute to scientific understanding of the comet's passage through the outer solar system. As 3I Atlas completes its crossing of the heliopause, it leaves behind the relatively stable environment of interstellar space and enters a dynamic region shaped by stellar activity, planetary gravitational fields, and the complex interactions between solar and galactic materials. This transition represents the beginning of the comet's brief but intense encounter with our solar system, marking the end of millions of years of quiet drift through the cosmic void and the start of a period of rapid change and evolution under the influence of solar radiation and gravity. Jupiter's immense gravitational field extends far beyond its visible disk, creating invisible currents in space-time that influence the motion of objects across the entire outer solar system. For 3I Atlas, approaching on its hyperbolic trajectory from interstellar space, the giant planet serves as both navigator and accelerator, subtly bending the comet's path while adding energy to its motion through gravitational interactions that have governed celestial mechanics since the solar system's formation. This encounter represents the most significant gravitational perturbation the comet will experience during its passage through our stellar neighborhood, demonstrating on a cosmic scale the same principles that allow spacecraft to gain velocity through planetary flybys. The planet's gravitational influence becomes measurable when 3I Atlas reaches a distance of roughly 10 astronomical units from Jupiter, still farther than Saturn orbits from the Sun, yet close enough for the giant planet's mass to begin affecting the comet's trajectory in detectable ways. Jupiter contains more than twice the mass of all other planets combined, creating a gravitational field so strong that it dominates the outer solar system's dynamical environment. This gravitational dominance has shaped the architecture of the solar system for billions of years, clearing gaps in the asteroid belt, capturing families of Trojan asteroids, and deflecting countless comets onto new orbital paths. As the comet approaches, Jupiter's gravity creates what physicists describe as a gravitational focusing effect, slightly converging the trajectories of objects passing through the outer solar system. This focusing acts like an enormous lens made of curved space-time, concentrating the flux of interstellar visitors toward the inner planets. Without this effect, fewer interstellar objects would penetrate deep enough into the solar system to become visible from Earth, making discoveries like 3I Atlas significantly more rare. The giant planet thus serves as a cosmic lighthouse, guiding wayward travelers from the depths of space toward our astronomical instruments. The mathematics governing this gravitational interaction follow the same principles that describe all orbital mechanics, but applied to an object following a hyperbolic rather than elliptical trajectory. As 3I Atlas approaches Jupiter, it experiences an acceleration that increases its speed relative to the planet while simultaneously curving its path through space. The energy for this acceleration comes from Jupiter's own orbital motion around the Sun. The planet loses an infinitesimal amount of orbital energy, while the comet gains a significant boost to its velocity. This energy transfer, though utterly negligible compared to Jupiter's total orbital energy, demonstrates the fundamental conservation laws that govern all gravitational interactions. Tidal forces from Jupiter begin to act on the comet's nucleus as the distance between them decreases, though these forces remain far too weak to disrupt the comet's structure. The difference in gravitational acceleration between the comet's near and far sides creates stresses measured in tiny fractions of Earth's surface gravity, insignificant compared to the internal cohesion that holds the nucleus together. More massive comets have been known to fragment during close approaches to Jupiter, creating spectacular displays as their constituent pieces separate and develop independent comas. But 3I Atlas possesses sufficient structural integrity to survive this gentle gravitational massage unscathed. The planet's magnetosphere adds another layer of complexity to the interaction, though its effects on an electrically neutral object like 3I Atlas remain minimal. Jupiter's magnetic field, generated by convection currents in its metallic hydrogen interior, extends millions of kilometers into space and traps charged particles in radiation belts more intense than anything found around Earth. As the comet passes through the outer fringes of this magnetospheric environment, any charged dust particles in its vicinity experience acceleration and deflection, but the bulk of the comet's material remains unaffected by these electromagnetic phenomena. The gravitational encounter occurs over a period of several months, with the most significant deflection taking place during the few weeks when 3I Atlas passes closest to Jupiter's orbital path. Computer simulations reveal that, without this interaction, the comet would have followed a slightly different trajectory through the inner solar system, perhaps passing closer to Earth or approaching the Sun from a different angle. Jupiter's influence thus shapes not only the comet's future path, but also the observational opportunities available to Earth-based astronomers during its passage through the inner planetary region. Resonance effects, though weak for a hyperbolic visitor like 3I Atlas, still contribute subtle perturbations to the comet's motion. These resonances occur when the periods of different orbital motions create simple mathematical ratios, allowing small gravitational tugs to accumulate over time into measurable effects. For objects on elliptical orbits, such resonances can lead to dramatic changes in orbital shape and orientation over millions of years. But for 3I Atlas, following its one-time hyperbolic trajectory, these effects remain curiosities for dynamical theorists rather than practical influences on its motion. The timing of the gravitational encounter depends on the relative positions of Jupiter and the comet along their respective paths, creating a cosmic choreography that has been predetermined since 3I Atlas first entered the outer solar system. Jupiter completes its 12-year orbit around the Sun with clockwork precision, while the comet follows its mathematically predictable hyperbolic arc, ensuring that their closest approach occurs at a specific time and distance that can be calculated centuries in advance. This predictability allows astronomers to plan observational campaigns that take advantage of the gravitational focusing effect to study the comet under optimal conditions. The encounter also provides a natural experiment in gravitational physics, allowing astronomers to test their understanding of celestial mechanics against the observed behavior of an object from interstellar space. Any deviations from predicted trajectories might reveal previously unknown forces or properties of the comet itself, such as outgassing that creates tiny rocket-like accelerations or unusual mass distributions within the nucleus. So far, 3I Atlas has behaved exactly as gravitational theory predicts, confirming our understanding of how massive objects interact across the vast scales of the solar system. Other planets contribute smaller but still measurable perturbations to the comet's trajectory, with Saturn's gravity providing the second largest influence on 3I Atlas's motion. The combined gravitational effects of all the giant planets work together to shape the comet's path through the outer solar system, though Jupiter's contribution dominates the interaction. These multi-body gravitational effects require sophisticated computer simulations to calculate accurately, as the influences of different planets combine in complex ways that resist simple analytical solutions. The gravitational focusing effect that Jupiter provides has implications extending far beyond the motion of individual comets. This same mechanism influences the trajectories of asteroids, dust particles, and even spacecraft traveling through the outer solar system. It helps explain why certain regions of space seem to collect more debris than others, and why the inner solar system receives a steady flux of material from the outer reaches. Understanding these gravitational highways becomes crucial for predicting the long-term evolution of planetary systems and for planning future space missions that might seek to intercept other interstellar visitors. As 3I Atlas recedes from its closest approach to Jupiter's orbital region, the gravitational interaction gradually weakens, leaving the comet with a permanently altered trajectory and a slight increase in its velocity relative to the solar system. The energy gained during this encounter will carry the comet more rapidly through the inner planetary region and accelerate its eventual departure from the solar system. In this way, Jupiter serves not only as a gravitational guide, but as a cosmic accelerator, speeding the comet's journey through our stellar neighborhood while providing astronomers with enhanced opportunities to study this visitor from the depths of interstellar space. As 3i Atlas continues its inward journey, crossing the invisible boundary where solar radiation begins to overpower the ancient cold that has preserved its structure for millions of years, the first subtle signs of transformation begin to appear on its dark surface. The temperature of the nucleus, which has remained within a few degrees of absolute zero throughout its interstellar wandering, starts to climb as photons from our Sun penetrate the vacuum of space and deposit their energy into the comet's ice-rich materials. This heating occurs gradually at first, so slowly that weeks pass before astronomical instruments can detect the earliest wisps of gas beginning to escape from the warming surface. The process begins in the topmost layers of the nucleus, where solar radiation penetrates perhaps a few centimeters into the porous mixture of ice and dust that forms the comet's outer shell. Water ice, the most abundant volatile component, requires relatively modest heating to begin sublimation, the direct transition from solid to gas that bypasses the liquid phase entirely in the vacuum of space. At temperatures around -150 degrees Celsius, still colder than the coldest natural temperatures recorded on Earth, individual water molecules begin to vibrate with sufficient energy to break free from their crystalline bonds and escape into the surrounding emptiness. This initial sublimation proceeds at rates measured in mere grams per second across the entire nucleus surface, creating a tenuous atmosphere too thin to observe with most telescopes. The escaping water vapor carries with it microscopic dust particles that have been frozen into the ice matrix, creating the first components of what will eventually become the comet's spectacular coma and tail. These dust grains, ranging in size from nanometers to micrometers, reflect sunlight with greater efficiency than the dark nucleus surface, making them the first visible signs of the comet's awakening activity. Carbon dioxide ice begins sublimating at even lower temperatures than water, creating the earliest detectable gases in the comet's nascent atmosphere. This CO2 sublimation occurs first in areas of the nucleus that face the Sun directly, creating asymmetric outgassing patterns that vary with the comet's rotation period. As the nucleus tumbles through space, different regions experience varying amounts of solar heating, creating a complex pattern of activity that waxes and wanes with each rotation cycle. Ground-based telescopes begin to detect these early signs of activity as a faint brightening in the comet's apparent magnitude, marking the transition from inert interstellar wanderer to active comet. The escape velocity from 3i Atlas's surface measures only a few meters per second, far slower than the speeds achieved by sublimating gases heated to hundreds of degrees below zero. This means that virtually all gas molecules escaping from the nucleus possess more than enough energy to overcome the comet's weak gravitational field, creating an expanding sphere of gas and dust that grows larger with each passing day. The initial expansion velocities reach several hundred meters per second, carrying material away from the nucleus at speeds comparable to rifle bullets. Though in the weightless environment of space, these particles follow ballistic trajectories determined by their initial velocities and the subtle pressure of solar radiation. Different volatile compounds sublimate at different rates and temperatures, creating a complex chemistry in the emerging coma as various molecular species escape from the warming nucleus. Carbon monoxide begins outgassing at temperatures even lower than carbon dioxide, while more exotic compounds like hydrogen cyanide and methanol require greater heating before they contribute significantly to the gas production. This sequential activation of different volatile reservoirs creates an evolving chemical composition in the coma that provides astronomers with information about the layered structure and thermal properties of the nucleus interior. Solar heating penetrates deeper into the nucleus as the comet continues its approach toward the inner solar system, activating subsurface ice deposits that may have remained frozen since the object's formation billions of years ago. The thermal wave propagates inward at speeds determined by the nucleus's thermal conductivity and porosity, reaching depths of several meters over the course of weeks. This subsurface heating can create internal gas pressures that eventually rupture through to the surface, producing jets of gas and dust that emerge from specific locations on the nucleus rather than from the entire illuminated hemisphere. The escaping gases interact with solar radiation in ways that make them visible to Earth-based telescopes equipped with appropriate filters and detectors. Water molecules absorb ultraviolet photons and re-emit them at visible wavelengths, creating a fluorescent glow that appears blue-green in photographs. Carbon monoxide produces different emission signatures, while dust particles simply reflect sunlight across all wavelengths, creating the whitish appearance typical of cometary Comet. These different emission mechanisms allow astronomers to separate the contributions of gas and dust to the comet's brightness and to estimate the relative abundances of different chemical species. Radiation pressure from sunlight begins to influence the motion of the smallest dust particles escaping from the nucleus, pushing them away from the sun and creating the first hints of what will eventually become a prominent dust tail. This radiation pressure acts more strongly on smaller particles, which have larger surface area to mass ratios, while larger grains follow trajectories determined primarily by their initial velocities and the gravitational influence of the solar system bodies. The result is a size-dependent sorting of dust particles that creates tails with different characteristics and orientations relative to the comet's motion through space. The comet's rotational motion becomes more apparent, as asymmetric outgassing creates subtle changes in brightness that repeat with each rotation period. These brightness variations result from the preferential heating of different regions of the nucleus as it tumbles through space, combined with variations in the surface properties that may reflect the comet's complex formation and evolutionary history. Photometric observations reveal a rotation period of approximately 18 hours, somewhat longer than typical for solar system comets, but consistent with the slow rotation expected for objects that have experienced minimal tidal interactions during their lifetimes. Gas dynamics in the inner coma create complex flow patterns as molecules escape from the nucleus and interact with solar radiation and magnetic fields. The initial radial expansion gives way to more complex motions as different gas species expand at different rates and as solar wind particles begin to ionize some of the gas molecules. These ionized species respond to magnetic fields in ways that neutral molecules do not, creating the potential for multiple distinct tail structures as the comet's activity level continues to increase. Thermal modeling of the nucleus suggests that the heating process will accelerate dramatically as 3I Atlas approaches closer to the Sun, with gas production rates potentially increasing by orders of magnitude over the coming months. The dark surface materials that cover much of the nucleus act as efficient solar absorbers, converting sunlight into heat that drives the sublimation of subsurface ices. However, the same dark materials may also form insulating layers that protect deeper ice deposits from heating, creating a complex interplay between surface properties and subsurface ice preservation. Spectroscopic analysis of the emerging gases provides the first direct measurements of isotopic ratios in materials formed around another star, offering unprecedented insights into stellar nucleosynthesis and planetary formation processes in distant stellar systems. The deuterium to hydrogen ratio in water vapor reveals information about the temperature and radiation environment where the comet's ice first condensed, while carbon and nitrogen isotope ratios reflect the nuclear burning history of the comet's parent star. These measurements represent some of the most direct evidence available for the chemical evolution of matter in other stellar neighborhoods. The transition from dormant nucleus to active comet marks a fundamental change in 3 Udi Atlas's relationship with its environment, As the object begins to interact dynamically with solar radiation, magnetic fields, and charged particle flows rather than simply moving passively through space. This awakening process, driven by the same solar energy that powers Earth's climate and biosphere, transforms the ancient wanderer into a temporary but spectacular member of our solar system's dynamic population of active bodies, creating phenomena visible across millions of kilometers of space while gradually depleting the volatile materials that have survived unchanged since the comet's formation in the distant past. The formation of tails represents one of the most visually spectacular aspects of cometary evolution, as the modest gas and dust production from 3I Atlas's warming nucleus transforms into vast streamers that extend millions of kilometers behind the traveling comet. These tails develop through the interaction of escaping material with solar radiation and the solar wind, creating structures so large they could span the distance between Earth and the Moon several times over, yet so tenuous that the entire mass of both tails combined weighs less than a small mountain. The physics governing their formation involves forces operating across enormous ranges of scale, from the molecular processes that liberate individual gas molecules from the nuclear surface to the galactic magnetic fields that help shape the solar wind flowing past the comet. Two distinct tail types emerge as the comet's activity level increases, each responding to different physical forces and displaying characteristic colors, shapes, and orientations. The gas tail, composed primarily of ionized molecules stripped of electrons by solar ultraviolet radiation, appears blue in photographs due to the fluorescent emission of carbon monoxide, ions excited by solar photons. This plasma tail points almost directly away from the Sun regardless of the comet's direction of motion, following magnetic field lines embedded in the solar wind like a cosmic weather vane that reveals the invisible architecture of interplanetary space. The dust tail develops simultaneously but follows different physical principles, as microscopic particles escaping from the nucleus respond to radiation pressure from sunlight rather than to magnetic forces. This tail appears yellowish-white in color, reflecting the same spectrum of solar radiation that illuminates the planets, and curves gently away from the comet's orbital path as the particles gradually separate from the nucleus. The curvature results from the combination of the particles' initial velocities, which carry them away from the nucleus in roughly radial directions, and the steady acceleration provided by solar radiation pressure acting over periods of days and weeks. Radiation pressure affects dust particles according to their size, with smaller grains experiencing stronger acceleration relative to their mass than larger particles. This size-dependent sorting creates a fan-shaped dust tail with the smallest particles pushed farthest from the orbital path and the largest grains following trajectories that remain closer to the comet's original direction of motion. The resulting structure resembles a cosmic broom sweeping through space, with different-sized particles spreading out like bristles of varying stiffness responding to the steady wind of solar photons. The gas tail forms through a more complex process involving the ionization of neutral molecules escaping from the nucleus, followed by their acceleration by magnetic fields frozen into the solar wind plasma. Solar ultraviolet radiation strips electrons from water, carbon monoxide, and other molecules, creating ions that become coupled to the magnetic field lines threading through the solar wind. These field lines act like invisible cables that drag the ionized gas away from the comet at velocities approaching the solar wind speed of several hundred kilometers per second, much faster than the initial escape velocities of the molecules when they first left the nucleus surface. Magnetic reconnection events can cause dramatic changes in the gas tail structure, sometimes severing the tail entirely and allowing a new tail to form as fresh, ionized material streams away from the nucleus. These disconnection events occur when the polarity of the solar wind magnetic field reverses, causing the field lines that thread through the comet's ionosphere to snap and reconfigure themselves. The disconnected portion of the tail continues moving away from the Sun while a new tail begins forming, creating spectacular time-lapse sequences when captured by sensitive cameras over periods of hours or days. The brightness of both tails depends on the rate of gas and dust production from the nucleus, which in turn depends on the amount of solar heating and the availability of volatile materials near the surface. As 3I Atlas continues its approach toward the inner solar system, both tails grow brighter and longer, potentially reaching maximum development around the time of perihelion when solar heating achieves its greatest intensity. Computer models suggest that the gas tail might extend tens of millions of kilometers at peak activity, while the dust tail could stretch even farther as radiation pressure continues to accelerate particles long after they escape from the nucleus. The internal structure of the tails reveals complex dynamics as different components respond to varying forces and environmental conditions. The gas tail often displays streamers and knots that reflect instabilities in the solar wind flow and variations in the comet's gas production rate. These structures evolve rapidly, sometimes changing dramatically over periods of hours as magnetic field configurations shift and as different regions of the nucleus experience varying amounts of solar heating due to rotational effects. Dust particles within the dust tail continue to evolve after leaving the nucleus, with the smallest grains potentially fragmenting under the stress of rapid heating by solar radiation or electrostatic forces generated by their charging in the solar wind environment. This secondary fragmentation can create cascades of even smaller particles that respond more strongly to radiation pressure, contributing to the complex brightness and color variations observed across the tail structure. Laboratory studies of meteoritic materials provide insights into the mechanical properties and thermal behavior of dust grains similar to those escaping from cometary nuclei. The interaction between the two tail types creates additional complexity as ionized gases and charged dust particles influence each other through electromagnetic forces. The plasma environment created by the gas tail can affect the charging and dynamics of dust particles, while the presence of dust can influence the electrical conductivity and magnetic field structure within the gas tail. These coupling effects become most important in the inner coma region close to the nucleus, where particle densities reach their highest values and collision rates between different species become significant. Seasonal effects influence tail development as different regions of the nucleus experience varying amounts of solar illumination depending on the orientation of the comet's rotation axis relative to its orbital plane. If 3I Atlas possesses significant obliquity, analogous to the axial tilt that creates Earth's seasons, then different hemispheres of the nucleus will experience enhanced heating at different points along the orbital trajectory. These variations could create asymmetric tail development and time-variable gas production rates that reflect the complex interplay between orbital mechanics and nuclear geology. The chemical composition of the gas tail provides detailed information about the nucleus composition through spectroscopic analysis of emission lines from different ionic species. Each type of ion emits characteristic wavelengths when excited by solar radiation, creating a fingerprint that reveals the relative abundances of water, carbon monoxide, carbon dioxide, and more exotic species like hydrogen cyanide and methanol. These measurements allow astronomers to probe the interior composition of a body formed around another star, providing direct evidence for the chemical conditions that prevailed during planetary formation in a distant stellar system. Anti-tails occasionally develop when viewing geometry creates the illusion of material extending toward the Sun rather than away from it. These apparent anti-tails result from the perspective effect created when Earth passes through or near the orbital plane of the comet, allowing observers to see dust particles that were ejected weeks or months earlier and have since spread out along the comet's orbital path, The anti-tail phenomenon demonstrates how the three-dimensional structure of cometary debris fields can create complex and sometimes counterintuitive appearances when viewed from changing vantage points. Both tails serve as natural laboratories for studying fundamental plasma physics and dust dynamics under conditions impossible to replicate in terrestrial experiments. The scales involved, the ultra-high vacuum environment, and the complex interplay of magnetic, gravitational, and radiation forces create phenomena that advance scientific understanding of processes operating throughout the universe. The tails of 3I Atlas thus represent not only spectacular visual displays, but also invaluable scientific resources that expand human knowledge of physics operating under extreme conditions in the cosmic environment. Perihelion approaches with the mathematical inevitability of celestial mechanics, marking the moment when 3U Atlas will reach its closest distance to the Sun and experience the most intense solar heating of its entire existence. At this cosmic turning point, roughly 1 astronomical unit from our star, the same distance that separates Earth from the Sun, the comet will receive solar radiation 1,300 times more intense than it experienced during its millions of years wandering through interstellar space. This dramatic increase in energy input drives the nucleus to peak activity levels, transforming what began as gentle wisps of escaping gas into a dynamic, rapidly evolving system of comas and tails that stretches across tens of millions of kilometers of space. The nucleus surface temperature climbs toward its maximum values as solar photons bombard the dark, organic-rich materials that coat much of the comet's exterior. These carbonaceous compounds, processed by millions of years of cosmic ray bombardment during the interstellar journey, absorb solar energy with remarkable efficiency, converting electromagnetic radiation into heat that penetrates several meters into the nucleus interior. Surface temperatures may reach -50 degrees Celsius in the most intensely illuminated regions, still far below the freezing point of water on Earth, but warm enough to drive vigorous sublimation of water ice and the more volatile carbon dioxide and carbon monoxide ices embedded throughout the nucleus structure. Gas production rates increase exponentially with rising temperature, following the fundamental physics of sublimation kinetics that govern the transition from solid to vapor phases. Computer models suggest that 3I Atlas may be producing several tons of water vapor per second at perihelion, along with comparable quantities of dust particles entrained in the escaping gas flows. This material expands away from the nucleus at velocities approaching 1 kilometer per second, creating a coma that grows to encompass a volume larger than many planets, while maintaining a density so low that the entire visible atmosphere contains less mass than a modest Earthbound lake. The comet's apparent brightness reaches its peak during the perihelion passage, making it potentially visible to moderately sized telescopes as solar illumination and increased activity combine to maximize the amount of sunlight reflected and scattered by the coma and tail materials. The brightness enhancement results from multiple factors operating simultaneously: more intense solar illumination, increased gas and dust production, and the geometric effect of decreasing distance from Earth-based observers. Photometric measurements reveal brightness variations that correlate with the comet's rotation period, indicating that different regions of the nucleus possess varying levels of activity and volatile content. Spectroscopic observations during perihelion passage provide the most detailed chemical analysis possible of materials formed around another star. The intense solar heating drives sublimation of volatile species that remain frozen at larger distances, revealing trace compounds that may preserve information about the original composition of the comet's parent protoplanetary disk. Hydrogen cyanide, methanol, ethane, and other complex organic molecules appear in the spectrum, their emission lines carrying isotopic signatures that reflect the nuclear burning history of the comet's birth star and the chemical evolution of its stellar neighborhood. The dust tail reaches maximum brightness and extension during this period, as radiation pressure from the intense solar illumination accelerates particles to their highest velocities and pushes them farthest from the comet's orbital path. The tail structure becomes increasingly complex as particles of different sizes follow diverging trajectories, creating the characteristic curved, fan-shaped appearance that can extend across several degrees of sky when viewed from Earth. The largest dust particles, millimeters to centimeters in diameter, follow trajectories that remain relatively close to the comet's orbit, while submicron grains experience such strong radiation pressure that they may eventually escape the solar system entirely. Jet activity becomes most pronounced during perihelion passage as localized regions of the nucleus develop enhanced gas production rates due to variations in composition, thermal properties, or surface topography. These jets appear as narrow streams of gas and dust emanating from specific locations on the nucleus, often persisting for periods of hours to days before shifting to different locations as the nucleus rotation exposes fresh surface areas to solar heating. High-resolution imaging reveals the collimated nature of these jets, which may originate from subsurface cavities or fractures that focus the escaping gas into narrow beams. The plasma environment surrounding the comet becomes increasingly complex, as higher gas production rates create a denser ionosphere that interacts more strongly with the solar wind. Magnetic field measurements reveal the development of a bow shock upstream from the nucleus, where the solar wind encounters the obstacle presented by the comet's expanding gas cloud and deflects around it like water flowing around a rock in a stream. This interaction creates a magnetosphere-like structure around the comet, though one far more dynamic and variable than the stable magnetic fields that surround planets like Earth and Jupiter. Thermal modeling of the nucleus interior suggests that heat conduction during perihelion passage may activate volatile reservoirs several meters below the surface, creating internal gas pressures that could lead to explosive outgassing events or even structural changes in the nucleus. The low thermal conductivity typical of cometary materials means that temperature changes propagate slowly inward, creating thermal gradients that persist for weeks after the peak heating at perihelion. These subsurface thermal effects may continue driving activity long after the comet begins its outward journey from the inner solar system. Solar wind interactions reach their maximum intensity during perihelion passage as the comet encounters the densest and most energetic portion of the particle stream flowing from the Sun. The solar wind pressure may reach levels sufficient to noticeably compress the gas coma on the sunward side while allowing it to expand more freely in the anti-solar direction. This asymmetric pressure distribution contributes to the formation of the characteristic teardrop shape observed in many active comets, with the narrow tail extending away from the Sun and the broader coma facing toward the solar wind source. Dust dynamics become increasingly important as higher production rates create particle clouds dense enough to influence their own evolution through collective effects. Electrostatic charging of dust grains in the solar wind plasma creates forces that can either enhance or oppose the radiation pressure acceleration, depending on the grain sizes and charging conditions. These electromagnetic effects add complexity to the dust tail structure and may contribute to the formation of narrow dust streamers, or the development of multiple tail components with different orientations and brightness distributions. The volatile depletion process accelerates during perihelion passage as the most accessible ice deposits near the nucleus surface sublime away, potentially exposing deeper layers with different compositions or creating a lag deposit of non-volatile materials that could alter the surface properties for any future solar approaches. However, since 3I Atlas follows a hyperbolic trajectory that will carry it permanently away from the solar system, this represents the only opportunity for solar heating to access the volatile materials preserved within its structure since formation around a distant star billions of years ago. Ground-based observatories coordinate intensive monitoring campaigns during the perihelion period, taking advantage of the enhanced brightness and activity to conduct detailed studies impossible at other times. Telescopes around the world maintain nearly continuous surveillance, tracking changes in brightness, tail structure, and spectral characteristics that occur on timescales of hours to days. These observations provide unprecedented insights into the real-time evolution of a comet under peak solar heating conditions, while simultaneously offering the unique opportunity to study materials formed in another stellar system. The perihelion passage represents not only the climax of 3I Atlas's brief visit to the inner solar system, but also the moment of maximum scientific opportunity for human civilization to learn about planetary formation processes operating around other stars. The intensive heating and activity driven by our sun's radiation serves as a natural laboratory experiment, breaking down the comet's structure and releasing materials that have remained unchanged since their condensation in a distant protoplanetary disk, providing direct evidence for the chemical and physical conditions that govern planet formation throughout the galaxy. The most sophisticated instruments humanity has ever deployed for astronomical observation turn their electronic eyes toward 3I Atlas as it reaches peak brightness and activity near perihelion. Space-based telescopes. Free from the atmospheric interference that limits ground-based observations, begin systematic campaigns to dissect the comet's composition with unprecedented precision. These instruments represent the culmination of decades of technological advancement in detector sensitivity, spectral resolution, and orbital mechanics, allowing astronomers to probe the chemical fingerprints of materials formed around another star with a level of detail that would have seemed impossible just a generation ago. The Hubble Space Telescope, orbiting 400 kilometers above Earth's surface, captures high-resolution images that reveal the detailed structure of the nucleus and inner coma region. Its advanced cameras, sensitive to wavelengths from ultraviolet through near-infrared, document the day-to-day evolution of jet activity as different regions of the nucleus respond to varying solar heating. The telescope's pointing stability, measured in milliarc seconds, allows for precise photometry that tracks brightness variations caused by the comet's rotation and by changes in gas and dust production rates from specific surface features. Infrared observations from space-based platforms provide thermal maps of the nucleus surface, revealing temperature distributions that reflect variations in thermal inertia, composition, and subsurface structure. These thermal measurements, conducted at wavelengths where the nucleus radiates its own heat rather than merely reflecting solar illumination, offer insights into the physical properties of materials that condensed from gas and dust around a distant star billions of years ago. The thermal emission spectra also reveal the presence of silicate minerals and organic compounds through their characteristic vibrational signatures in the mid-infrared wavelength range. Ultraviolet spectroscopy becomes particularly valuable during the comet's active phase, as solar radiation excites gas molecules escaping from the nucleus to fluoresce at specific wavelengths that identify individual chemical species. The characteristic green emission of diatomic carbon, the blue fluorescence of carbon monoxide ions, and the ultraviolet signatures of water dissociation products create a spectroscopic fingerprint that reveals not only which molecules comprise the comet's atmosphere, but also their relative abundances and physical conditions. These measurements provide direct evidence for the inventory of volatile materials available during planetary formation in the comet's birth system. High-resolution spectrometers analyze the fine structure of emission and absorption lines with sufficient precision to measure Doppler shifts that reveal the three-dimensional velocity structure within the comet's coma. These velocity measurements map the expansion of gas away from the nucleus. the rotation of the gas cloud as it inherits angular momentum from the spinning nucleus, and the acceleration of ionized species by magnetic fields embedded in the solar wind. The resulting velocity maps provide insights into gas dynamics processes that operate under conditions impossible to replicate in terrestrial laboratories. Radio telescopes contribute observations at longer wavelengths. Detecting emission from hydroxyl radicals produced when solar ultraviolet radiation dissociates water molecules escaping from the nucleus. These radio observations can penetrate dust clouds that obscure optical observations, providing complementary information about gas production rates and the distribution of water vapor throughout the extended coma. The radio emission also reveals information about the magnetic field structure within the comet's ionosphere through the polarization characteristics of the detected signals. Isotope ratio measurements represent perhaps the most scientifically valuable observations possible during the comet's active period, as they preserve information about nuclear processes that occurred within the comet's parent star and the chemical evolution of its stellar neighborhood. Mass spectrometry techniques applied to high-resolution spectra can distinguish between different isotopes of carbon, nitrogen, oxygen, and sulfur, revealing ratios that reflect the particular mix of stellar nucleosynthesis products available when the comet's materials first condensed from a protoplanetary disk around another star. The deuterium to hydrogen ratio in water vapor provides especially important constraints on the formation environment, as this ratio depends sensitively on the temperature and radiation conditions present during ice condensation. Preliminary measurements suggest a DH ratio different from that found in Earth's oceans or in most solar system comets, though the uncertainties remain large enough to permit various interpretations. More precise measurements may eventually reveal whether the comet formed in a stellar environment with deuterium enrichment similar to or different from that which characterized the early solar nebula. Dust analysis employs multiple techniques to characterize the solid particles escaping from the nucleus, ranging from direct imaging of individual grains to statistical studies of their size distributions and optical properties. Polarization measurements reveal information about particle shapes and compositions, while multi-wavelength photometry provides insights into size distributions and scattering properties. Some observations attempt to detect the infrared emission signatures of specific mineral phases within the dust grains, potentially revealing the high-temperature condensation history of rocky materials formed in the inner regions of the comet's birth system. X-ray observations, though challenging due to the comet's relatively low activity level, may detect emission from highly ionized species created when solar wind particles interact with gas molecules in the comet's atmosphere. These X-ray signatures provide information about the charge state distribution of heavy ions in the solar wind and about the efficiency of charge exchange processes that transfer electrons between solar wind ions and neutral gas molecules escaping from the nucleus. Such measurements contribute to understanding both cometary physics and solar wind composition. Temporal monitoring reveals the dynamic nature of cometary activity as gas production rates, jet orientations, and dust emission patterns change in response to nuclear rotation, solar heating variations, and subsurface thermal evolution. Time series photometry tracks brightness variations with periods ranging from hours to weeks, revealing not only the basic rotation period of the nucleus, but also more complex periodicities that may reflect the activation and deactivation of specific surface regions as they rotate into and out of solar illumination. Spectropolarimetry combines spectroscopic and polarization measurements to provide additional constraints on the physical properties of gas and dust in the comet's atmosphere. The degree and orientation of polarization depend on the scattering properties of dust particles and on magnetic field orientations within ionized gas regions, providing information that cannot be obtained through intensity measurements alone. These observations become particularly valuable for studying the magnetic field structure within the comet's plasma environment and the alignment properties of elongated dust particles. Coordinated observations from multiple observatories allow for nearly continuous monitoring during critical periods when rapid changes in activity occur. Ground-based telescopes distributed around the Earth provide coverage throughout each 24-hour period, while space-based instruments add observations at wavelengths blocked by Earth's atmosphere. This global coordination ensures that transient phenomena such as outbursts, disconnection events, or changes in jet activity can be captured and studied in detail. The data collected during these intensive observational campaigns will require years of analysis to fully interpret, as astronomers work to extract maximum scientific information from each spectrum, image, and photometric measurement. Computer models that simulate cometary activity under various assumptions about nucleus composition and structure will be tested against the observations, potentially revealing new insights into the physics of sublimation, gas dynamics, and dust transport processes operating under the extreme conditions found in cometary environments. Perhaps most significantly, these observations of 3I Atlas represent humanity's first detailed study of materials formed around another star, providing direct evidence for the chemical and physical processes that govern planetary formation throughout the galaxy. The comet serves as a natural laboratory that brings samples of another stellar system within reach of our most advanced analytical techniques, expanding scientific understanding of cosmic chemistry and stellar evolution far beyond the narrow perspective provided by solar system materials alone. The detection of complex organic molecules within the expanding coma of 3I Atlas marks one of the most profound scientific discoveries of the encounter, as spectrometers identify carbon-based compounds that formed in the primordial chemistry of a distant stellar system and survived the long journey through interstellar space intact. These molecules, ranging from simple two-carbon species to complex chains containing nitrogen, oxygen, and sulfur atoms, represent direct samples of the organic inventory available during planetary formation around the comet's parent star. Their presence confirms that the fundamental chemical processes leading to biological complexity operate not just in our own solar system, but throughout the galaxy wherever conditions permit the formation and preservation of carbon-based chemistry. Hydrogen cyanide emerges as one of the most abundant organic species detected in the gas spectra, its characteristic emission lines appearing prominently in ultraviolet and infrared observations as solar heating drives sublimation of HCN ice from subsurface regions of the nucleus. This molecule, composed of hydrogen, carbon, and nitrogen atoms arranged in a linear configuration, represents one of the fundamental building blocks of prebiotic chemistry. On Earth, hydrogen cyanide serves as a precursor to amino acids, nucleotide bases, and other biomolecules under appropriate chemical conditions, making its detection in an interstellar comet particularly significant for understanding the cosmic distribution of life's chemical prerequisites. Methanol appears throughout the coma in concentrations that rival those of more common volatile species like carbon dioxide, indicating that alcohol chemistry played an important role in the comet's formation environment. This simplest of alcohols, containing a single carbon atom bonded to 3 hydrogen atoms and 1 hydroxyl group, forms readily in cold, dense molecular clouds, where carbon monoxide ice reacts with hydrogen atoms over periods of thousands to millions of years. Its abundance in 3I Atlas suggests that the comet either formed in such a molecular cloud environment or incorporated materials that had been processed in interstellar space before the formation of its parent stellar system. Formaldehyde detection adds another piece to the organic chemistry puzzle, as this simple aldehyde represents both a product of methanol oxidation and a precursor to more complex organic synthesis reactions. The molecule's presence indicates that oxidation-reduction chemistry operated within the comet's formation environment, possibly driven by radiation from nearby massive stars or by chemical reactions occurring on the surfaces of dust grains embedded in the protoplanetary disk. Formaldehyde also serves as an intermediate in reaction pathways that can lead to the formation of sugars and other biologically important compounds under appropriate conditions. More complex hydrocarbons appear in smaller quantities, but with significant implications for understanding carbon chemistry in extraterrestrial environments. Ethane, consisting of 2 carbon atoms bonded together with 6 hydrogen atoms, indicates that carbon-carbon bond formation occurred during the comet's formation or subsequent evolution. The presence of ethane alongside methane suggests a family of related hydrocarbon compounds that may extend to even more complex species below current detection limits. These hydrocarbons could serve as energy sources for hypothetical microorganisms, much as they do in Earth's deep subsurface environments. Ammonia detection provides evidence for nitrogen chemistry beyond the hydrogen cyanide already identified, indicating that nitrogen was available in multiple chemical forms during the comet's formation. Ammonia represents the simplest nitrogen-hydrogen compound and serves as a fundamental building block for amino acid synthesis in prebiotic chemistry scenarios. Its presence also affects the physical properties of ice mixtures, lowering freezing points and altering sublimation rates in ways that may influence the comet's activity patterns and the preservation of other organic species within the nuclear structure. Sulfur-bearing organic compounds add complexity to the chemical inventory, with hydrogen sulfide representing the most abundant sulfur species detected in the coma gases. Carbon disulfide and other sulfur-containing molecules appear in trace quantities, indicating that sulfur chemistry participated in the organic synthesis processes operating in the comet's formation environment. Sulfur compounds play important roles in biological systems on Earth, particularly in enzyme function and cellular metabolism, making their presence in interstellar materials relevant for understanding the cosmic distribution of biochemical potential. The isotopic composition of carbon within these organic molecules provides insights into their formation mechanisms and evolutionary history. Carbon-13 to carbon-12 ratios measured through high-resolution spectroscopy reveal whether the organic compounds formed through gas phase chemistry in the interstellar medium, through surface reactions on dust grains, or through thermal processing in the warm regions of a protoplanetary disk. Different formation pathways produce characteristic isotopic signatures that serve as forensic evidence for the chemical processes that created these complex molecules billions of years ago. Nitrogen isotope ratios within hydrogen cyanide and ammonia offer additional constraints on formation conditions. As the abundance of nitrogen-15 relative to nitrogen-14 depends on temperature, density, and radiation environment during molecular synthesis, these ratios may preserve information about the nuclear burning processes within the comet's parent star, as different stellar masses and metallicities produce distinctive nitrogen isotope signatures that become incorporated into planetary formation materials. Comparing these ratios with those found in solar system materials reveals similarities and differences in stellar nucleosynthesis between different galactic neighborhoods. Deuterium enrichment in organic molecules provides another diagnostic tool for understanding formation environments, as heavy hydrogen incorporation depends sensitively on temperature and chemical reaction rates. Deuterium-enriched organic compounds typically form in very cold environments, where reaction kinetics favor the incorporation of heavy isotopes, such as in molecular clouds or the outer regions of protoplanetary disks. The degree of deuterium enrichment measured in 3I Atlas organics may thus constrain the temperature and location where these molecules first formed around their parent star. Complex reaction networks linking these various organic species suggest that sophisticated chemistry operated within the comet's formation environment, potentially creating molecular inventories even richer than current observations can detect. Laboratory studies of cometary analog materials demonstrate that irradiation and thermal processing of simple organic mixtures can produce hundreds of different carbon compounds, many of which remain below current detection thresholds for astronomical observations. The molecules detected in 3I Atlas likely represent only the most abundant products of much more extensive organic chemistry. The preservation of these organic molecules throughout millions of years of interstellar travel demonstrates the remarkable stability of carbon-based chemistry under extreme conditions. Cosmic ray bombardment, ultraviolet radiation from distant stars, and the harsh vacuum of space all work to break down complex molecules over long time periods. Yet substantial quantities of organics survive the journey from another stellar system to our own. This preservation suggests that organic chemistry may be even more widespread and durable in the galaxy than previously suspected, with implications for the cosmic distribution of potentially habitable environments. Astrobiological implications emerge from these organic detections, as the molecular inventory found in 3I Atlas overlaps significantly with the chemical precursors thought necessary for the emergence of life as we understand it. While the presence of organic molecules does not indicate biological activity, it demonstrates that the chemical foundations for biology exist throughout the galaxy in environments far removed from any planetary surfaces. This organic inventory, delivered to planetary systems by comets and asteroids, may have played crucial roles in supplying the raw materials for prebiotic chemistry on countless worlds throughout cosmic history. The study of organic molecules in 3I Atlas represents a new frontier in astrobiology and cosmochemistry, providing direct access to the organic chemistry operating in another stellar system. These observations expand human understanding of carbon chemistry beyond the solar system, while demonstrating that the molecular building blocks of life represent a common feature of planetary formation throughout the galaxy. The comet thus serves not only as a messenger from distant stars, but as evidence for the universal nature of the chemical processes that may ultimately lead to biological complexity wherever suitable conditions develop. The geometry of celestial mechanics aligns to bring 3I Atlas within 35 million kilometers of Earth, closer than any previous confirmed interstellar visitor has approached our planet, offering astronomers an unprecedented opportunity to study materials from another stellar system with extraordinary precision. This cosmic close approach, occurring roughly 6 weeks after the comet's perihelion passage, positions the ancient wanderer at a distance less than 1/4 that separating Earth from the Sun, making it temporarily one of the closest non-terrestrial objects accessible to detailed observation. The combination of proximity and continuing activity from recent solar heating creates optimal conditions for the most comprehensive analysis ever conducted of truly alien materials within our solar system. Ground-based telescopes around the world coordinate their observations to maximize coverage during the close approach period, taking advantage of the comet's enhanced apparent brightness and angular size to conduct studies impossible at greater distances. The largest optical telescopes, equipped with adaptive optics systems that compensate for atmospheric turbulence, achieve spatial resolutions approaching the theoretical limits imposed by telescope aperture size. These high-resolution observations reveal structural details within the coma and tail system that provide insights into gas and dust dynamics operating on scales of hundreds to thousands of kilometers around the nucleus. Radar observations from planetary defense installations attempt to probe the nucleus directly, bouncing radio waves off the solid surface to measure rotation rates, shape parameters, and surface roughness characteristics. The techniques developed for studying potentially hazardous asteroids find new application in characterizing this visitor from interstellar space. Though the nucleus's small size and relatively large distance challenge the sensitivity limits of current radar systems, successful radar echoes would provide the first direct measurements of the nucleus's physical dimensions and rotation state, complementing the indirect estimates derived from optical brightness variations. Spectroscopic observations achieve their highest precision during the close approach, as increased signal strength allows for measurements of weak spectral features previously hidden in instrumental noise. High-resolution spectrographs detect subtle absorption and emission lines from trace species that comprise less than 1% of the total gas production, revealing molecular inventories that reflect the detailed chemistry of the comet's formation environment. These observations identify isotopic variants of common molecules and exotic chemical species that provide constraints on temperature, pressure, and radiation conditions in the comet's birth stellar system. Professional astronomers collaborate with advanced amateur observers around the globe to maintain nearly continuous photometric monitoring during the close approach period. This distributed observing network, coordinated through internet communications and standardized measurement protocols, generates time series data with temporal resolution measured in minutes rather than hours. The resulting light curves reveal rapid variations in brightness and activity that may correlate with specific surface features rotating into and out of solar illumination, providing information about the heterogeneous distribution of volatile materials across the nucleus surface. Space-based observatories adjust their scheduled observations to take maximum advantage of the enhanced observing conditions during close approach. The James Webb Space Telescope, operating at the Earth-Sun L2 Lagrange point, conducts detailed infrared spectroscopy that penetrates dust clouds and reveals thermal emission from the nucleus surface. These observations measure temperature distributions and thermal inertia values that constrain the physical properties of surface materials formed around another star, while simultaneously detecting organic molecules through their characteristic vibrational signatures in the mid-infrared wavelength range. Dust particle detection experiments attempt to collect or analyze individual grains escaping from the comet as Earth passes through the outer regions of its expanding coma. Specialized detectors mounted on high-altitude aircraft or balloon platforms sample the upper atmosphere for microscopic particles that may have originated from 3I Atlas and survived entry into Earth's atmospheric environment. While the chances of detecting such particles remain extremely small due to the comet's distance and the dilute nature of its dust production, any successful collection would provide laboratory access to materials formed around another star. Radio astronomy observations during close approach focus on detecting emission from exotic molecular species and studying the plasma environment surrounding the comet with enhanced sensitivity. Very long baseline. Interferometry networks achieve angular resolutions sufficient to map the distribution of hydroxyl radicals and other species within the inner coma, revealing details of gas dynamics and chemistry operating near the nucleus surface. These observations also search for possible radio emission from the nucleus itself, which might indicate electrical activity or unusual magnetic properties inherited from the comet's formation environment. Polarimetry measurements reach their highest precision during the close approach period, as increased signal strength allows for accurate measurement of the polarization characteristics of light scattered by dust particles in the coma and tail. These measurements reveal information about particle shapes, compositions, and size distributions that complement direct imaging and spectroscopic observations. The polarization signatures also provide insights into the magnetic field structure within ionized regions of the coma, where charged particles align themselves with local field directions and create distinctive polarization patterns in emitted light. Occultation opportunities arise when the comet passes in front of background stars as seen from Earth, allowing astronomers to probe the density and structure of the coma through measurements of stellar light attenuation. These natural experiments provide information about the three-dimensional distribution of gas and dust around the nucleus, revealing asymmetries and temporal variations that may reflect ongoing sublimation processes or interactions with the solar wind. The technique works best for bright background stars and requires precise timing coordination between multiple observing sites to map the coma structure. Thermal infrared observations during close approach achieve sufficient sensitivity to detect day-night temperature variations on the nucleus surface, potentially revealing information about thermal inertia, surface roughness, and subsurface structure. These measurements constrain the physical properties of materials that condensed from gas and dust around a distant star, providing insights into the formation and evolution processes that shaped the comet's structure over billions of years. Thermal modeling of the observations may reveal subsurface layering or composition variations that reflect the complex accretion history of the nucleus. International space agencies coordinate potential spacecraft mission concepts that could take advantage of the close approach to conduct even more detailed studies. Though the short timeline between discovery and closest approach limits the feasibility of dedicated missions, existing spacecraft in Earth orbit or at Lagrange points adjust their observing schedules to maximize scientific return from this rare opportunity. While mission planners develop concepts for future interstellar visitor encounters based on lessons learned from 3I Atlas observations, citizen science projects engage astronomy enthusiasts worldwide in coordinated observational campaigns that supplement professional observations with additional temporal coverage and geographic distribution. These projects democratize participation in cutting-edge astronomical research while generating scientifically valuable data through standardized observing protocols and centralized data analysis procedures. The combination of professional and amateur observations creates a comprehensive dataset that captures both large-scale evolutionary trends and rapid transient phenomena that might otherwise escape detection. The close approach represents a fleeting opportunity that will not repeat, as 3I Atlas follows its hyperbolic trajectory away from the inner solar system toward eventual departure from the solar system entirely. Every observation conducted during this optimal period contributes irreplaceable information about the composition, structure, and behavior of materials formed around another star, expanding human knowledge of planetary formation processes operating throughout the galaxy. The scientific legacy of these observations will continue growing for years as astronomers analyze the accumulated data and develop new theoretical models to explain the properties of this cosmic messenger. The proximity achieved during closest approach transforms 3I Atlas from a distant astronomical curiosity into an accessible laboratory for studying extraterrestrial materials formed under conditions that may differ significantly from those that prevailed during solar system formation. This natural experiment provides insights into the diversity of planetary formation processes while demonstrating the feasibility of detailed scientific investigation of future interstellar visitors that may approach even closer to Earth or remain visible for longer periods. The gravitational mathematics that brought 3I Atlas into our solar system now work with equal precision to carry it away. As the comet begins its long exit journey toward the outer darkness beyond Neptune's orbit, having rounded the Sun and experienced the most intense stellar heating of its existence, the ancient wanderer now follows the outbound portion of its hyperbolic trajectory with the same inexorable certainty that governed its approach. Solar gravity, which briefly accelerated the comet to its maximum velocity during perihelion passage, now acts as a gentle brake, gradually slowing its motion as distance increases, though never enough to prevent its eventual escape from our star's gravitational influence entirely. The comet's velocity, relative to the Sun, has reached its peak value of nearly 40 kilometers per second during the closest solar approach, carrying it fast enough to cross the continental United States in less than 2 minutes. This represents a substantial increase from the 26 kilometers per second with which it first entered the outer solar system. The additional energy gained through gravitational interaction with our star's immense mass. As 3U Atlas recedes from the inner planetary region, this velocity gradually decreases according to the conservation of energy, but it will never drop below the escape velocity needed to break free from solar gravity entirely. Activity levels begin their gradual decline as increasing distance reduces the intensity of solar radiation striking the nucleus surface. The exponential relationship between temperature and sublimation rate means that even modest decreases in solar heating translate into significant reductions in gas and dust production, causing the spectacular coma and tail structures to slowly fade and contract. This cooling process occurs gradually at first, taking weeks to become clearly apparent, but will accelerate as the comet moves beyond the orbit of Mars and solar heating drops below the threshold needed to maintain vigorous sublimation of water ice. The nucleus surface, heated to its maximum temperature during perihelion passage, begins the slow process of cooling back toward the frigid conditions that have characterized most of the comet's existence. Heat conduction into the interior continues for months after peak heating, gradually warming subsurface layers and potentially activating volatile deposits that were too deep to respond to the initial solar heating. This delayed thermal response may sustain some level of activity long after the comet has moved beyond the distance where fresh solar heating can drive significant sublimation, creating an extended period of declining but persistent gas and dust production. The dust tail, stretched across tens of millions of kilometers by radiation pressure during the active period, begins its own slow evolution as newly produced particles decrease in number while existing material continues to disperse along the comet's orbital path. The largest dust grains, less affected by radiation pressure, follow trajectories that remain relatively close to the comet's path, while the smallest particles continue accelerating away from the solar system under the influence of stellar photons. This size-dependent dispersal creates a gradually widening trail of material that may remain detectable for months or years after the comet itself has faded below observational limits. Jupiter's gravitational field influences the comet's outbound trajectory just as it affected the inbound path, though with reduced effect due to the increased velocity and different geometric configuration. The giant planet provides a final gravitational nudge that slightly alters the comet's exit velocity and direction, sending it toward a different region of interstellar space than it would have reached without this encounter. Computer simulations reveal that these subtle orbital perturbations will carry 3I Atlas toward the constellation Telescopium, though the uncertainties in position will grow to encompass large regions of sky over the millions of years required for the journey to the nearest stars. The gas tail begins to fade more rapidly than the dust tail as decreasing solar heating reduces the production of ionized species that create the characteristic blue fluorescent emission. The complex plasma physics that shape the gas tail during peak activity gradually simplifies as gas production rates drop below the levels needed to maintain strong interactions with the solar wind. What remains of the ionized gas continues to stream away from the comet at high velocity, but the diminishing supply of fresh material causes the visible tail to contract and eventually disappear entirely from telescopic view. Observational campaigns shift their focus from studying peak activity phenomena to documenting the decline of cometary processes as solar heating diminishes. These observations provide insights into the thermal inertia and subsurface structure of the nucleus. As different regions respond to decreasing solar input at different rates depending on their composition, porosity, and depth below the surface. The gradual fade of activity also reveals the baseline properties of the nucleus itself, allowing more accurate measurements of size, shape, and rotation characteristics as the overwhelming brightness of the coma diminishes. Outgassing patterns become increasingly asymmetric as the comet moves away from the Sun, with enhanced activity on the hemisphere that continues to receive direct solar illumination, while the opposite hemisphere begins its transition back toward interstellar cold. This asymmetry drives subtle changes in the comet's rotation state and trajectory, as the thrust from escaping gases creates small but measurable accelerations that slightly alter the predicted orbital path. These non-gravitational forces, though tiny compared to solar gravity, accumulate over time and require careful monitoring to maintain accurate predictions of the comet's future position. The transition from active comet back to inactive nucleus occurs gradually over a period of months. As solar heating drops below the threshold, temperatures needed to drive sublimation of different volatile species. Carbon dioxide stops sublimating first, as its higher vapor pressure requires less heating to maintain gas production, followed by water ice as surface temperatures drop below the critical values needed for vigorous sublimation. This sequential deactivation of different volatile reservoirs creates a changing chemical composition in the residual coma as the relative abundances of different species shift in response to their varying sublimation thresholds. Dust production continues at reduced levels even after gas production has dropped significantly. As thermal cycling and structural changes within the nucleus may cause mechanical fragmentation that releases particles without requiring active sublimation. These processes, driven by thermal expansion and contraction of different materials within the nucleus, may maintain a tenuous dust cloud around the comet long after visible gas production has ceased. The dust particles follow ballistic trajectories determined by their initial velocities and solar radiation pressure, creating a sparse but persistent coma that gradually disperses into the interplanetary medium. Radio observations become increasingly important during the fade period as they can detect trace amounts of gas production that may continue below the threshold for optical detection. Hydroxyl radical emission, produced by the photodissociation of water vapor, remains detectable at radio wavelengths even when the overall activity level has dropped to the point where visible light observations can no longer discern clear evidence of ongoing sublimation. These radio observations provide the most sensitive measure of residual activity as the comet transitions back toward dormancy. Scientific analysis of the accumulated observational data begins in earnest as the comet fades from easy visibility, with researchers working to extract maximum information from the months of intensive study conducted during the active period. Computer models that simulate cometary activity under various assumptions about nucleus composition and structure are tested against the observed behavior, potentially revealing new insights into the physics of sublimation, gas dynamics, and dust transport processes operating in these exotic environments. The outbound journey represents the final chapter of 3i Atlas's brief but scientifically productive visit to our solar system. Each passing day carries the comet farther from the Sun and closer to its eventual return to the interstellar medium, where it will resume the cold, dormant state that characterized most of its multi-million-year journey from another stellar system. The wealth of scientific data collected during its passage will continue to yield insights for years to come, providing humanity's most detailed look at materials formed around a distant star and preserved in the cosmic deep freeze of interstellar space. The exit trajectory will carry 3i Atlas beyond the orbits of the outer planets over the coming years, past the heliopause boundary where solar influence gives way to interstellar conditions, and eventually into the galactic void where it will continue its wandering journey among the stars. This departure marks not an ending, but a transition, as the comet returns to the vast cosmic ecosystem of objects traveling between stellar systems, carrying with it whatever subtle changes its encounter with our Sun may have produced in its ancient structure and composition. The inexorable progression of celestial mechanics carries 3i Atlas beyond the realm of the giant planets, past the scattered disk objects that mark the solar system's ragged edge, and toward the heliopause boundary where our Sun's influence finally yields to the galactic medium from which the comet originally emerged. Telescopes around the world maintain their vigilant watch as the wanderer fades week by week, its apparent brightness diminishing according to the inverse square law that governs the illumination of distant objects. The comet that once blazed with the reflected glory of solar radiation and the fluorescent emission of an active coma now appears as little more than a stellar point of light, distinguishable from background stars only by its subtle motion against the celestial sphere. At distances approaching 30 astronomical units from the Sun, farther than Neptune, orbits our star. The comet experiences solar heating too feeble to drive significant sublimation of even the most volatile ices embedded within its nucleus. Surface temperatures have dropped to levels approaching those of the interstellar void, perhaps negative 200 degrees Celsius, cold enough to freeze nitrogen and oxygen into solid form. The dramatic transformation from active comet back to dormant nucleus occurs gradually but irreversibly, as the thermal energy accumulated during perihelion passage slowly radiates away into the cosmic cold that has dominated the object's existence for millions of years. Professional observatories equipped with the largest apertures and most sensitive detectors continue tracking the fading visitor. Pushing their instruments to the limits of detection capability, photometric measurements become increasingly challenging as the comet's brightness drops below the threshold where statistical noise begins to dominate signal strength, requiring longer exposure times and more sophisticated data analysis techniques to extract meaningful information from the sparse photons collected by telescope mirrors. These observations document the final stages of the transition from spectacular active comet to invisible interstellar wanderer. The last detectable traces of cometary activity manifest as faint emission from residual gas molecules still escaping from the cooling nucleus at rates perhaps 10,000 times lower than during peak activity near perihelion. Radio telescopes sensitive to hydroxyl, radical emission continue detecting these molecular signatures weeks after optical telescopes can no longer discern any evidence of ongoing sublimation processes. These radio observations provide the most sensitive measure of the comet's gradual return to dormancy, revealing the slow decrease in gas production as solar heating drops below the critical thresholds needed to maintain sublimation of water ice and other volatile compounds. Astrometric measurements become the primary observational technique as the comet fades beyond the limits of spectroscopic analysis, with precise position measurements allowing astronomers to refine their understanding of the object's trajectory and predict its future path through interstellar space. These positional observations, accurate to small fractions of an arcsecond, contribute to orbital solutions that will remain valid for millions of years into the future. Tracking the comet's progress as it journeys toward the constellation Telescopium and eventually beyond the gravitational sphere of influence of any individual star, computer simulations project the comet's future path through the galaxy, taking into account the gravitational influences of nearby stars, the rotation of the galactic disk, and the large-scale structure of dark matter that shapes the motions of stellar systems over cosmic timescales. These calculations suggest that 3i Atlas will spend the next several million years crossing the relatively empty regions between stellar systems, gradually cooling toward the cosmic background temperature while traveling distances measured in parsecs rather than astronomical units. The simulations also predict occasional encounters with molecular clouds or stellar wind boundaries that may provide brief episodes of heating or electromagnetic interaction during the otherwise quiescent journey through interstellar space. Ground-based survey telescopes continue their search patterns in hopes of detecting other interstellar visitors that may follow 3I Atlas through the solar system. Using the observational techniques and data analysis methods refined during study of this cosmic messenger, the discovery and characterization of 3I Atlas has demonstrated both the scientific value of such objects and the technological capabilities needed to detect and study them, encouraging expanded efforts to identify additional examples of this exotic class of solar system visitors. Statistical models suggest that several interstellar objects larger than a few hundred meters may pass through the inner solar system each year, though most remain too faint for detection with current instrumentation. The accumulated scientific data from months of intensive observation begins yielding insights that extend far beyond the specific properties of 3I Atlas itself, contributing to broader understanding of stellar evolution, planetary formation, and galactic chemical evolution. Isotopic measurements provide constraints on nuclear burning processes in other stellar types, while organic molecule detections expand knowledge of carbon chemistry operating under conditions very different from those found in our own solar system. These results influence theoretical models of how planetary systems form around different classes of stars and how material gets exchanged between stellar systems through the galactic ecosystem of wandering objects. Amateur astronomers equipped with modest telescopes contribute final observations as the comet approaches the limit of visibility for smaller instruments, adding to the global dataset that documents its complete passage through the solar system. These observations, coordinated through internet networks and standardized measurement protocols, extend the temporal coverage of professional observations while demonstrating the value of distributed observational networks for tracking faint, rapidly moving objects. The collaborative effort between professional and amateur astronomers established during the 3I Atlas campaign provides a model for future studies of similar interstellar visitors. Archive searches through decades of astronomical survey data begin the process of identifying possible prediscovery images of 3I Atlas, potentially extending the observed orbital arc backward in time and improving the precision of trajectory calculations. These archival studies, enabled by digital storage of astronomical images and sophisticated automated detection algorithms, may reveal that the comet was actually captured on photographic plates or electronic detectors months or years before its official discovery. Though at brightness levels too faint to trigger detection at the time of the original observations, theoretical work inspired by the 3I Atlas observations explores the implications of interstellar object discoveries for understanding the population dynamics of small bodies throughout the galaxy. Models of planetary system formation predict that gravitational interactions during the early evolution of stellar systems should eject large numbers of comets and asteroids into interstellar space, creating a vast population of nomadic objects traveling between the stars. The detection rate of such objects in our solar system provides observational constraints on these theoretical predictions, while offering insights into the efficiency of planet formation processes operating around other stars. Laboratory analysis of meteorites and cosmic dust particles takes on new significance in light of detailed characterization of 3I Atlas composition. As researchers search for evidence of interstellar materials that may have reached Earth's surface through previous encounters with similar objects. While the vast majority of meteorites originate from solar system sources, statistical arguments suggest that occasional fragments from interstellar visitors should be represented in terrestrial collections. Though identifying such exotic samples requires sophisticated analytical techniques capable of recognizing subtle isotopic and chemical signatures that distinguish truly alien materials from solar system natives. The fading comet serves as a natural laboratory for testing observational techniques and data analysis methods that will prove crucial for studying future interstellar visitors, particularly those that may be discovered earlier in their solar system passage and thus remain visible for longer periods. The lessons learned from 3i Atlas observations inform the design of future survey telescopes and spectrographs optimized for detecting and characterizing these rare but scientifically valuable objects. While the accumulated expertise in rapid response observational campaigns prepares the astronomical community for more intensive studies of subsequent discoveries, as winter approaches in the Northern Hemisphere and 3i Atlas continues its relentless recession toward the outer darkness, the comet that briefly illuminated humanity's understanding of interstellar chemistry and planetary formation processes slowly returns to invisibility. The ancient wanderer resumes its cosmic journey much as it began, cold, dark, and solitary, carrying within its frozen structure the chemical fingerprints of a distant stellar neighborhood while heading toward an uncertain future among the stars. Only the scientific legacy of its passage remains, preserved in thousands of images, spectra, and measurements that will continue revealing insights about the galaxy's chemical evolution for decades to come. The scientific legacy of 3i Atlas extends far beyond the months of active observation, as laboratories around the world begin the painstaking work of analyzing meteorite collections for particles that may have originated from previous interstellar visitors. Advanced mass spectrometry techniques, developed originally for studying samples returned from solar system missions, now turn their precision toward identifying isotopic signatures that could mark truly alien materials among the thousands of extraterrestrial samples housed in research institutions. While the probability of finding such exotic specimens remains vanishingly small, the potential scientific value justifies exhaustive searches through meteorite databases and museum collections for objects with chemical compositions that fall outside the known range of solar system materials. Theoretical models of galactic chemical evolution incorporate new constraints provided by the detailed composition measurements of 3i Atlas, refining understanding of how stellar nucleosynthesis products get distributed throughout the galaxy over cosmic time. The isotopic ratios measured in the comet's water, organic molecules, and rocky components provide direct sampling of stellar nucleosynthesis operating under different metallicity conditions, potentially revealing information about the age and formation history of the stellar neighborhood from which the comet originated. These measurements contribute to broader efforts to understand how chemical complexity has evolved throughout the galaxy's history and how the ingredients for planet formation vary between different stellar environments. Database archives of astronomical observations spanning decades undergo systematic reanalysis using detection algorithms optimized for identifying faint, fast-moving objects that may represent additional interstellar visitors previously overlooked in the original data processing. Digital sky surveys conducted over the past 20 years contain billions of images that can be searched retrospectively for objects with motion and brightness characteristics consistent with interstellar origin. This archaeological approach to astronomical data may reveal that interstellar visitors are more common than previously recognized, with many objects passing through the solar system undetected due to their faintness or unfavorable observing geometry. The organic molecule inventory detected in 3i Atlas becomes a reference standard for astrobiological research, providing the first direct measurement of carbon chemistry operating in another stellar system. Laboratory experiments attempt to replicate the formation pathways for these molecules under conditions thought to prevail in protoplanetary disks around different types of stars, testing theories about how organic complexity develops during planetary system formation. The detection of hydrogen cyanide, methanol, formaldehyde, and other prebiotic precursors in an object from another star strengthens arguments that the chemical foundations for life may be widespread throughout the galaxy. Computer simulations trace the galactic orbits of objects ejected from different types of stellar systems, attempting to identify the most likely source regions for interstellar visitors like 3I Atlas, based on their chemical compositions and dynamical properties. These models incorporate the complex gravitational environment of the galaxy, including spiral arm structure, stellar density variations, and the influence of massive molecular clouds that can perturb the trajectories of small objects over millions of years. The goal is to develop a cosmic forensics capability that can link interstellar visitors back to their probable origins, providing insights into planetary formation processes operating around different classes of stars. Technological development efforts focus on designing instrumentation optimized for rapid characterization of future interstellar visitors, learning from the observational challenges encountered during the 3I Atlas campaign. Space-based telescopes specifically configured for Comet science could provide continuous monitoring capability free from atmospheric interference and the day-night cycle that limits ground-based observations. Proposed instruments include high-resolution spectrographs capable of detecting weak emission lines from trace species, thermal infrared cameras for measuring nucleus temperatures and thermal inertia, and dust analyzers that could characterize individual particles escaping from active comets. International space agencies begin preliminary studies for dedicated interstellar visitor intercept missions, recognizing that such objects provide unique opportunities to study materials formed around other stars with spacecraft-based instruments. The short warning time between discovery and solar system exit poses significant challenges for mission design, requiring either pre-positioned spacecraft capable of rapid trajectory changes or revolutionary propulsion technologies that could reach high velocities quickly. Alternative approaches focus on deploying networks of small spacecraft throughout the outer solar system to maximize the probability of close encounters with future interstellar visitors. Educational initiatives incorporate the 3I Atlas discovery into astronomy curricula at all levels, using this concrete example of interstellar material to teach concepts ranging from orbital mechanics and spectroscopy to stellar evolution and astrobiology. The Comet's journey provides a narrative framework for explaining how gravitational forces operate across different scales, how chemical elements formed in stellar cores get dispersed throughout the galaxy, and how scientific instruments extract detailed information from faint sources of electromagnetic radiation. These educational applications ensure that the scientific legacy of the discovery extends beyond research publications into broader public understanding of cosmic processes. Citizen science projects continue monitoring the positions of known interstellar objects and searching for additional examples among the millions of sources detected by all-sky surveys. Volunteer astronomers, equipped with modest telescopes, contribute observations that extend professional monitoring capabilities, while image analysis projects engage participants in searching through archived survey data for moving objects that may have been missed by automated detection algorithms. These collaborative efforts demonstrate how modern astronomy benefits from distributed observational networks and crowdsourced data analysis capabilities. The dust trail left by 3I Atlas during its passage through the inner solar system may remain detectable for years, as microscopic particles continue following their radiation pressure-modified trajectories through interplanetary space. Spacecraft equipped with dust detectors could potentially encounter these particles and conduct in situ analysis of truly interstellar material, providing chemical and isotopic measurements with precision impossible to achieve through remote spectroscopic observations. Such encounters would represent humanity's first direct physical contact with materials formed around another star. Refined statistical estimates of the interstellar object population suggest that several dozen such visitors may pass through the inner solar system each century, though most remain too faint for detection with current survey capabilities. Next-generation telescopes, including extremely large ground-based instruments and space-based surveys with unprecedented sensitivity, should dramatically increase the discovery rate while providing enhanced characterization capabilities for detected objects. The Vera Rubin Observatory, with its ability to survey the entire visible sky every few days, may detect dozens of interstellar visitors over its planned operational lifetime. Theoretical work on planetary system dynamics incorporates lessons learned from 3I Atlas to refine models of how gravitational interactions during system formation eject comets and asteroids into interstellar space. These studies suggest that virtually every planetary system should contribute to the galactic population of wandering objects, with ejection rates depending on planetary masses, orbital configurations, and stellar encounter frequencies. The detection of interstellar visitors in our solar system thus provides observational constraints on planet formation, efficiency, and system architecture throughout the galaxy. Archival storage and curation of all observational data related to 3I Atlas ensures that future researchers will have access to complete datasets for reanalysis using improved techniques and theoretical understanding. Digital repositories maintain raw images, reduced spectra, and derived measurements in standardized formats designed for long-term preservation and accessibility. This data stewardship recognizes that the scientific value of interstellar visitor observations may continue growing for decades as new analysis methods and theoretical frameworks develop. The brief visit of 3I Atlas has fundamentally expanded human perspective on the solar system's place within the broader galactic community, demonstrating that our stellar neighborhood participates in ongoing exchange of materials with distant regions of the galaxy. This cosmic metabolism, operating over timescales of millions to billions of years, connects the chemical evolution of our solar system to processes occurring around other stars, creating a galactic ecosystem where stellar death and birth continuously redistribute the elements necessary for planet formation and potentially for life itself. The comet's legacy lives on in the scientific literature, where its measured properties will serve as benchmarks for understanding interstellar object populations and constraints for theoretical models of planetary system formation throughout the galaxy. More broadly, its discovery and characterization represent a milestone in humanity's efforts to understand our cosmic context, providing direct evidence that the chemical processes governing planet formation operate similarly around other stars while revealing the dynamic nature of the galactic environment in which all stellar systems evolve. The ancient wanderer has returned to the darkness between stars, but its brief illumination by our sun has permanently enriched human understanding of the cosmos we inhabit. The solar system settles back into its ancient rhythms, the gravitational harmonies that have governed planetary motions for 4.5 billion years resuming their timeless dance. The orbits of worlds continue their measured progressions, Mercury racing through its 88-day circuit, Earth maintaining its steady course through seasons of change, the giant planets moving with stately dignity through their decades-long journeys around the distant sun. Yet, something has shifted in this cosmic choreography. Something subtle but profound, as if the very space between the worlds retains the memory of an ancient visitor's passage. In the depths beyond Neptune's realm, where sunlight fades to little more than starlight and temperatures approach the absolute cold of interstellar space, the traces of 3I Atlas's presence disperse into invisibility. Microscopic dust particles, liberated from ice matrices that formed around a distant star billions of years ago, follow their own ballistic trajectories through the outer solar system. These motes of alien matter, each no larger than a bacterium, carry within their crystalline structures the chemical signatures of stellar nucleosynthesis that occurred in galactic neighborhoods far from our own. They drift in the cosmic dark, following paths determined by radiation pressure and gravitational influences, too subtle for human instruments to detect. The heliopore's boundary, that invisible membrane where solar influence yields to interstellar conditions, has been crossed once again by material that originated beyond our star's domain. But now, the flow reverses where once an intact nucleus of ice and rock penetrated inward toward the solar fires. Now only wisps of gas and scattered grains make their outward journey toward the galactic void. The solar wind continues its endless expansion, carrying with it traces of elements forged in our sun's core, mingling these solar products with the ancient interstellar materials liberated from the comet's structure during its brief period of activity. Deep space, that realm of emptiness between the worlds, returns to its accustomed stillness. The gravitational waves that mark the passage of massive objects settle back to the imperceptible tremors caused by planetary motions and solar oscillations. Magnetic field lines, briefly perturbed by the comet's ionosphere, realign themselves according to the steady architecture imposed by solar rotation and the galaxy's vast magnetic structure. The medium through which light travels, space itself, bears no permanent record of the visitor's passage, returning to the same quantum vacuum state that has characterized the solar system's interior for geological ages. Radio telescopes around Earth continue their patient listening, but the characteristic emission signatures of hydroxyl radicals and carbon monoxide ions have faded below detection thresholds. The cosmic radio background, that faint hiss of electromagnetic radiation left over from the universe's creation, once again dominates the signals received by sensitive antennas. Occasionally, a distant pulsar's beacon sweeps across Earth's position, or a stellar flare brightens some far-off star's radio emission. But the specific frequencies that once marked an interstellar visitor's presence have returned to the realm of thermal noise and instrumental uncertainty. The data archives grow quiet, their servers storing terabytes of images and spectra that captured a cosmic encounter spanning mere months in a universe aged nearly 14 billion years. These digital records preserve the scientific legacy of the visit, but the phenomenon they document has passed beyond the reach of direct observation. In astronomical terms, 3i Atlas has become history, a past event encoded in measurements and memories, rather than an ongoing presence in Earth's night sky. Scientists continue their work in laboratories and at computer terminals, analyzing the accumulated observations and developing theoretical models to explain what they witnessed. But the universe has moved on, as it always does, following physical laws that operate with indifference to human curiosity and wonder. Stellar evolution continues in the distant stellar nursery where the comet was born, with massive stars burning through their nuclear fuel and scattering heavy elements into the interstellar medium. New planetary systems condense from gas and dust clouds enriched by countless previous generations of stellar death and rebirth. Somewhere in the cosmic deep, beyond the reach of any human instrument, 3i Atlas continues its solitary journey through the galaxy. Its surface cools toward the background temperature of space, its rotation gradually slowing due to the subtle torques exerted by electromagnetic radiation from distant stars. The nucleus tumbles through the void, carrying within its ancient structure a record of chemical processes that operated under conditions slightly different from those that governed solar system formation. This cosmic message in a bottle drifts toward an uncertain future, perhaps to encounter other stellar systems in the far distant future, or perhaps to wander between the stars until the galaxy itself evolves beyond recognition. The solar system breathes its cosmic breath, the eternal expansion and contraction of solar wind pressure, as stellar activity waxes and wanes with the 11-year magnetic cycle. Comets native to our system continue their own eccentric orbits, some approaching the Sun to develop temporary comas and tails before retreating to the cold outer reaches where they formed. Asteroids pursue their gravitationally determined paths through the inner planetary region, occasionally perturbed by planetary encounters, but fundamentally unchanged by the brief visit of an interstellar interloper. Earth turns on its axis, carrying observatories through the cycle of day and night, through seasons of varying stellar visibility. The planet's magnetic field deflects the solar wind and cosmic rays with the same efficiency it has maintained for billions of years, protecting the biosphere from radiation while allowing electromagnetic signals to penetrate the ionosphere and reach ground-based receivers. Life continues its own evolutionary journey, largely unaware that materials from another stellar system briefly shared the same cosmic neighborhood. Time flows onward in its steady progression, measured by atomic clocks and planetary motions, marked by the gradual decay of radioactive isotopes and the patient expansion of the universe itself. The visit of 3I Atlas becomes part of the larger tapestry of cosmic history, another thread woven into the ongoing story of matter and energy redistributing themselves according to fundamental physical principles that operate across all scales of space and time. The darkness between stars reclaims another wanderer, as it has reclaimed countless objects throughout galactic history. The ancient patterns of stellar birth and death, of gravitational clustering and tidal dispersal, continue their eternal cycles. In this vast cosmos, where galaxies themselves are temporary structures, the brief illumination of a single comet represents just one moment in the endless dance of matter through space and time. Silence returns to the solar system, a quietude broken only by the whisper of solar wind through the interplanetary medium and the distant songs of radio waves from cosmic phenomena beyond human comprehension. In this cosmic stillness, the memory of an ancient visitor fades into the background of astronomical history, leaving behind only the scientific knowledge gained from its passage and the profound reminder that our solar system exists within a galaxy filled with wandering worlds.